Okay, so good afternoon. So we are going to start our last session of this conference, and this session will be chaired by Professor Archan Majumdar from SN Bose Institute.
Thank you, Pankaj. So let's start the afternoon session, and all of you know it's a long session, and so we'll be pressed for time, and it doesn't help matters that a large number of speakers are online. So I would again request everybody to respect punctuality. So let us now invite Professor Urvashi Sinha from Raman Research Institute to Bangalore, and Urvashi needs no introduction to this audience. So Urvashi, you have 30 minutes for your talk. And since you are not here, I can't warn you before, I can't give you a prior warning, but I know that you will finish well in time. So Urvashi.
Thank you so much, Professor Majumdar and Orchunda, if I may. This is the second time I'm speaking in Kolkata in perhaps the same year in some sense, and you are chairing the session. So I think it is an extra privilege. I'm very sorry that I couldn't be there, in person. I just returned a day or so back from the UK, and another trip was a little bit difficult to make, given that I had almost missed half the conference. So, but thanks a lot. I'm hoping the conference is going very well, and I can add a little bit to it with the work that we have done on secure semi-device independent QRNG via LGI violations from photonic systems to superconducting qubits. This is, of course, as Ochunda already mentioned, I mean, of course, we have been at this business for a while now. In India, just celebrated 13 years of our lab. And so we have done quite a bit of work in various areas of quantum, but today's focus is on quantum communications and specifically on random number generation in a different way that we have done over the last few years. This is a nutshell, so various activities in quantum communications, quantum computing, quantum sensing, as well as precision tests of foundations of quantum mechanics and quantum gravity. Going on to the topic of the talk, which is on random number generation. And of course, it's the last day, last session of this particular conference. So this is a question that I'm quite sure we are asking each other, even if I am virtually there, that quantum is here and there and everywhere, and what does quantum mean for you and me? Of course, we have these beautiful conferences now. We are celebrating 100 years of quantum. But then still, are we in a state of superposition? I hope I am in a state of entanglement with the audience that is in Kolkata. But then, in principle, we don't really tunnel through a wall. And so these features that we talk about in quantum, do they really make sense to us, macroscopic beings? And of course, can we test quantum in the macro limit? Of course, and this is a question which has been asked by great people, for instance, Albert Einstein, who says that he likes to think, or said that I like to think the moon is there even if I'm not looking at it. And this is the reference, by the way, for that quote. And this brings us to the concept of realism, which is essentially something very, very puzzling. Just like superposition and tunneling, realism is very puzzling because it suggests that something should have a predefined property, right? So all of us, have predefined properties irrespective of what others are doing, so irrespective of the act of measurement, objects should have a predefined property. But that is not the case in quantum, as we know. And for instance, a qubit happens to be in either 0 or 1 till we measure it. And that, of course, forms the basis for the quantum computer. So in some sense, many things that are commonplace in quantum, are not so in classical or let's say the realist world. And so realism is one such concept. And I think this audience very well knows the concept of realism. But then comes these things as to how do we test, or how does nature differentiate between micro and macro? And of course, local realism, local realist inequalities, we know of bipartite or multipartite systems and the inequalities, the Bell and Bell type inequalities, very, very well known, inequalities and tests and so on. But the question that Anthony Leggett asked was, what happens to a single system? A single system is not going to be, bipartite or multipartite in that sense. So how are we going to test for its realism? And so that brings us to this concept of what is called macro realism, which applies to single systems. Okay, and so there we are using what is called the superposition principle. Of course, we know what that is. And here the important thing is that a single system, while it cannot be in, let's say, two places at the same time, it can be, it can actually evolve in time. And so we can form inequalities which are now based on time rather than the spatial separation. And so that is what brings us to what are called the Leggett-Garg inequalities. Okay, so this brings us also to the Nobel Prize in Physics 2022, which was given to Alan Aspey, John Clauser, and Anton Zeilinger. And of course, there are groups for these pioneering experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Now, a little pause that, this particular Nobel Prize was very special, not only because, we are working in this field, but also because, it was given to, I would say, persistence. So these people didn't do the experiments in a day or a month or a year. So something like this takes decades, and something that our funding agency should take note a little bit, that certain things take some time, and we should give scientists a little bit of time to do something out of the ordinary. And of course, why did the other two? I mean, of course, John Clauser did the first experiment, but Alan Aspey and Anton Zeilinger and their groups, they spent a lot of time and energy in closing what are called the loopholes in these Bell inequality experiments. And if you wanted to know a little bit and didn't want to read all the experimental papers, then this is a review that I was invited to write, which is not half bad, which the students can have a look at. So loophole-free Bell tests, of course, this was the Zeilinger one, and there were others in the same year. So why is a loophole-free test such an important achievement? Of course, and this is again a beautiful article in Physics Today, which I didn't write, but it's nonetheless very nice. Of course, it's very nice because it tells you that there are no remaining doubts about the underlying theory being real and complete. That is good. But then it also has a practical motivation, which is very nice, because a loophole-free Bell test demonstrates not only that particles can be entangled at all, but also that a particular source of entangled particles is working as intended and hasn't been tampered with. And so this is the point. So an eavesdropper cannot come and use that loophole to come up with some, counter, attack on whatever it is that you're trying to do in secure quantum communications, whether it's QKD or unhackable sources of truly random numbers. And so this is the basis for all these beautiful experiments which followed on loophole-free, with the loophole-free Bell tests. Which brings us to our humble contribution, which is based on the Leggett-Garg inequality and our loophole-free test of macrorealism, which was done with heralded single photons and published in Jan 2022, which was the first loophole-free violation of the Leggett-Garg inequalities. And of course, it was a great privilege for us to be able to do this experiment, given that lots of years and decades have been spent in, again, closing loopholes similar to the Bell situation. And now these are being used for secure quantum communications like the Bell inequalities. And, so locality and realism gives you Bell inequalities. Likewise, realism and non-invasive measurability gives you macro realism. So realism remains. You replace locality with something else because, of course, locality doesn't make much sense. When you have a single particle, it's obviously going to be local. So non-invasive measurability is the assumption that is used for the derivation of the Leggett-Garg inequalities, which is a temporal analog of the Bell's inequality in terms of space-time, time-separated correlation functions corresponding to successive measurement outcomes for a system whose state evolves in time. Now, notion of realism is invoked in deriving LGI by assuming that a system during its time evolution is at any given time in a definite one of macroscopically separated available states. Very important sentence here. So here is where we define this macroscopic superposition, that you have to be able to clearly distinguish between the two possibilities that this system is in, which is, of course, a superposition state that we are defining. So this macroscopic separation needs to be well established. And the other thing which needs to be well established is NIM, or non-invasive measurability, which is a very hard thing to establish experimentally, of course, because we are saying that, in principle, it is possible to determine which of the states the system is in without affecting the state itself or the system's subsequent dynamics, and non-invasive measurement. Very hard problem, because measurements in principle tend to be a little bit invasive. And so these are the two concepts that we need to satisfy for LGI experiments. So original motivation was, for probing what I said earlier, which is to test the limits of quantum mechanics in mesoscopic macroscopic regime. Example, experiments involving the ISQIC device. So various experiments have happened where people have, increased the mass of an object little by little and tried to see where LGI may break down. Recent years, the quantum mechanical violation of LGI and its implications have been extensively studied for various types of microsystems to test their non-classicality. Okay, from single qubits, solid-state qubits, nuclear spins, electrons, photons, so on and so forth. All this without invoking the notion of locality. So this is our experiment, which is done using hereditary single photons, as I mentioned. It's the first loophole-free experiment where both LGI and WLGI inequalities have been violated. It's a comprehensive refutation of the classical realist worldview. Another important aspect of this experiment is that, we took into account painstakingly all the experimental non-idealities and came up with a modified bound for LGI within quantum mechanical predictions. Okay, because if you violate realism, for instance, in the bell, it is not necessary. It is only quantum mechanics which will satisfy that. It could be some other theory also which may satisfy, the violation of local realism. But here we actually matched it perfectly with quantum mechanical predictions. Okay, and then finally, of course, we proved unambiguously the non-classicality of single photon states. And so this is the, I don't have much time to go through details, as is obvious. It's not a very long talk. So LGI is in a time separated events. So T1, T2, T2, T3, T1, T3. And so the QM bound is 1.5 quantum mechanics. And from macro realism, it is less than equal to 1, just like your 2 and 2 root 2 for the CHSH bell for students who are not familiar with the LGI terms. WLGI is the Wigner form, and that has the QM bound of 0.5. Now we did both because both are necessary but not sufficient conditions of macrorealism. So simultaneous is good because it's more robust. Secondly, an experimental reason, the LGI requires 12 measurements, okay, of joint probabilities. WLGI requires 3. And of course, as experimentalists, whether you believe it or not, we like to do as little experiments as possible because each experiment adds error. And so this was also another reason why we did both. Okay, and so this was the concatenated Mach-Zehnder geometry, and so this is T1, the first time, and then the second one is T2, and then beyond the third beam splitter is T3. The upper and lower arms of the Mach-Zehnder define the two states that the photon can be in. So these are your macroscopically distinct states, the upper and the lower arms, and the macroscopicity parameter in this case is the ratio between the spatial separation of these arms to the wavelength of the photon, which is as high as 10 to the 4. A very important point, that macroscopicity does not necessarily only mean increasing masses. It is a situation dependent problem or definition. And so here it is a length scale dependent one. In the SQUID one, it was ratio of the clockwise and anti-clockwise flux and so on. And so this was a very high macroscopicity, and we actually dealt with all these very known loopholes that were plaguing the LGI experiments and closed or circumvented them for the first time. Okay, and so this was the actual schematic. This is an example of several experiments where clumsiness loophole has been attacked before, but then the other loopholes have not garnered much attention till then, especially detection efficiency loophole, which actually plays a critical role in many Bell violation experiments. And so we of course closed all of them together, right? And this is an important slide. It gives you the results. So this is the experimentally measured value, and this is the quantum mechanically predicted range, including the experimental non-idealities, and you can see an almost perfect match. And so this is what pleased us immensely. And of course, the NSIT, the no signaling in time, which we actually satisfied in order to give you a stronger closure of the clumsiness loophole than just the negative result measurements. And so this was also very well satisfied. So based on this, as I mentioned, the first application that we ourselves have done is a single system based generation of certified randomness using violations of the Leggett-Garg inequality. And so this was using our loophole free experiment that we did with photons. And of course, it opens up an unexplored avenue towards an empirically convenient class of reliable random number generators harnessing the quantumness of single systems. Okay, so now random numbers, they are very important for various things, but very importantly, they are used in to ensure security of encrypted communications and digital signatures and so on. So for cryptography, random numbers play a very crucial role, and that is where we need this higher solutions, let's say, for generating randomness. These are all other examples, but generation of random numbers is not particularly straightforward. and understanding them and their properties is essential for effective and reliable use. The pseudo-random number generators are all around us. Okay, and so this is an example of how you can just use a MATLAB code or something and generate them. Problem, they are deterministic, they are periodic, they are good, they are efficient, of course, because they produce many numbers, but that's not very nice because you see the security depends on the complexity of the algorithm and seed. They're not truly random and they're predictable enough not to be used in secure purposes such as cryptography. So then that brings us to true random number generators, and this is something I did not come up with. I don't know what is true about them. They're essentially physical random number generators, as I would like to call them, but the community named it TRNG. So this is randomness from an entropy source. These are examples. This is an important example. For instance, a photon on a beam splitter, which is 50-50. 50% probability of transmission, 50% probability of reflection. So this gives you a great random number generator. So these are all examples of physical random number generators, including this example that I gave of a QRNG. But what is the problem with them? Well, the problem is that, okay, so you have an input, you have this true random number generator, you have this bit stream. Well enough. Now, I have used, let's say, a QRNG and generated this. But you can come and do something simple like a memory stick attack. Okay, so you can just copy this and then again use that as a source of randomness. So essentially, the problem is that we cannot certify the randomness from the bit stream because we can't certify whether this bit string has been generated from a really random source or not. Okay, and so this is one important problem that these different classes of RNG that we have talked about so far face. And of course, they are also physical, which means that they would age with time and so they would become unreliable anyway. So that is another detail. They're device dependent, obviously. But certification is a big concern. And so this brings us to device independent certified randomness. And of course, Bell inequality violation has been used for doing this for the last many years now. And so Bell inequalities, I will skip. You all know this. Locality and realism gives Bell inequality. But this is an important paper. I think it's a beautiful paper by Cavalcanti and Weisman, where they use predictability and no signaling, as assumptions to again derive Bell inequality. Okay, and so what this means is that if you violate Bell inequality, then of course you can violate no signaling or predictability, but you cannot violate no signaling because it is of course a fundamental law of nature. So then violating Bell inequality gives you a natural violation of predictability, which gives you a source of random numbers. Okay, and this has been used, and so this is a slide which gives you the chronology of seminal experiments in this domain. This was the first one, right, by Pironio et al., which was a proof of concept. It was not loophole free or anything. Then we went on to the loophole free ones, small number of bits, larger number of bits. But what is important here is that for all these loophole free based random number generation using Bell, the spatial separation is of the order of 200 meters because you need that to close the locality loophole. Otherwise, you can, signal to each other, right? And which is something that is a loophole. So this is a fundamental problem because, imagine having a device which is 200 meters long. Is not very efficient, and that is why our work comes in here, because we have used Leggett-Garg inequality, which is a single system-based randomness generation and correlations in time, so spatial separation becomes irrelevant. Okay, and so this is what we went on to show here, and the Leggett-Garg inequalities, we've just done that. This is the circuit way of defining them. And now predictability and NSIT can be likewise used to generate, to derive Leggett-Garg inequality. So if I violate LGI, while maintaining no signaling in time, then I'm violating predictability, which gives me a source of random numbers. And in fact, the experimental architecture that I discussed earlier was precisely that. We had violated LGI while painstakingly satisfying no signaling in time. And that gives us this source of random numbers. Okay, and of course, how do you do this? You of course have to do this using an entropy calculation. Details are all in this publication. I have maybe 5 more minutes of speaking time, so I won't go through much of the detail, but then this is going to be subject to the LGI conditions. Then you can generate the amount of randomness. One thing to note that in our randomness generation, we have certain assumptions like the dimensional system being 2, projective measurements at T1 and T2, generalized POVM at T3, and also initial state is not correlated with any other system. So these actually make us say that our randomness generation is semi-device independent. That is what you'll find in our paper, but of course we want to go towards a regime where it becomes device independent later. And so we have done the bound on genuine randomness. Okay, and so this is the graph. So genuine randomness as a function of LGI violation, 1 to 1.5 is obviously the range. So at 1, you have 1 bit of randomness, but as you go up to 1.5, you can have up to 1.4 bits of GR. Likewise, we have also done the analysis that we want security against state preparation. So for instance, initial state might be attacked by an eavesdropper. Let's say initial state is entangled with Eve state. So then we use conditional probabilities and figure out the new bound with this secure state preparation assumption. And here, of course, genuine randomness will drop. So instead of 1 to 1.4, you'll have 0 to 0.4, but still it will be an appreciable amount of randomness. NSIT is something we need to satisfy, as I have already mentioned. But suppose, in an experiment, you can't do anything perfectly, naturally. And so then suppose there is a little bit of, violation of the NSIT conditions. Then what would happen? So we have analyzed that. And as you can see, as we keep on increasing this amount, our genuine randomness will drop, but, it will still remain appreciable. Likewise, memory effect. In order to estimate the LGI violation, we need to repeat the experiment multiple times. Each run might not be independent. Statistical analysis is to account of the memory effect. So then we have done the accounting of the memory effect as well. And so this is what happens: lower genuine randomness in the presence of memory effect, as might be expected, and even lower randomness for biased selection of input. So all these calculations are there in this publication that you see, along with, of course, the experiment which generates the random numbers, which is something I just discussed. So these are the correlations that we are measuring as a part of the experiment. And I'll show you the results. So we conducted 1,000 runs, and these were the results which we just saw. Skip that and go straight to the table, which tells you. So these are the various bits we generated for each of these 8 sub-runs. And so we have around 1 million bits and around 4,000 bits per second, which is actually very nice because, of course, that wasn't the aim of this experiment. The aim of the experiment was to prove that we can generate random numbers by violating Leggett-Garg inequality in a loophole-free architecture. And so this is what we have done. And of course, we will do other things. So semi-device independent generation of RNG using temporal correlations doesn't require the large spatial separation and preservation of entanglement over distance. Important point: loophole-free experiment to generate bits at an appreciable rate, secure against any attacks on the initial state. And next would be rigorous estimation, taking into account possible side information and employing extraction and amplification in the future. Very recently, not very recently, but in the beginning of February, this was released on the archive, currently under review. We have generated certified random numbers using quantum computers. Okay, and so this was again done by violating Leggett-Garg inequality on commercially available quantum computer, and this was the circuit there. And so you can see this is the LGI violation, and this is genuine randomness as a function of LGI violation. One thing you will notice: this is our theoretical prediction, and the generated results are always a little bit lower than the theory. And of course, we spent a lot of time and energy on figuring out the error analysis for this with a lot of help from IBM. And so you can see now here the modified. So once you take into account this error mitigation strategies in explicit detail, you can see that they match very closely with the theoretical prediction, which tells you that the random numbers that we have generated are not from a classical error, which was very important for us. And so that is what we spent a lot of time and energy on. So we have certified randomness on a quantum computer using LGI violations for the first time, serves as a fundamental validation of quantum mechanics on a quantum computer, and practical application for benchmarking quantum devices. Very interestingly, last week we had a paper appear on the archive and in a journal simultaneously, where they have used a different technique on a quantum computer to generate random numbers. So suddenly this topic has become very interesting, and I'm glad that our paper has been on the archive for some time and it's under review. Hopefully the kind of excitement that suddenly this new paper has also generated just adds to this community building up with time. So this is us with Tony Leggett, and of course, New Scientist called us the most watertight experiment of all time. Just a couple of minutes, the last 2 minutes I have, I want to say that this is a conference on quantum optics, information and communication. So I am very privileged again to be leading one of the 14 successful technology groups under India's National Quantum Mission, where we are working on a multi-node quantum repeater network for entanglement distribution-based quantum communication. So here we have collaborations with several institutes and IIT Patna, IIT Tirupati, HRI Prayagraj, and ISER Mohali, and together we are going to build different kinds of quantum memories using different platforms and then bring them together to show multi-node quantum repeater network. and that is our aim. And I have also co-founded a startup now almost a year ago, where we are taking some of these ideas from lab to market. And this is the team, which consists of quantum scientists, engineers, as well as people from the business background. And we are very pleased with our developments, which are at a very reasonable TRL level right now. And we hope to take all this forward as a part of NQM. And so this is my group. And so if you want to come and join us, of course, I'm also building a new lab at University of Calgary. So we will have literally, 13,000 kilometers of travel for any student or postdoc who joins my lab, and different fantastic environments to explore. So thank you very much, Orchunda. I think I'm on time. I don't know if Orchunda has gone to sleep. Okay, yeah, great.
Very nice talk. And we have some time for questions, comments. Right. So by the time somebody thinks of a question, let me ask you a very obvious question.
Sure. Yeah.
How do your randomness generation compare with the generation using the standard Bell test, for example? And in the same spirit, does this method have any, apart from, of course, its originality, does this have any operational advantage over a Bell violation-based randomness generation?
Yes, absolutely it does. And of course, great question. So a Bell violation-based random number generation is one thing, but if you want to actually have a random number generation, which is, based on a loophole-free Bell violation experiment, which is what we want, of course, because we don't want any loopholes in whatever we do. Then, as I just explained a few slides earlier, currently with the technology that we have available, doing a loophole-free Bell experiment requires around a couple of 100 meters of separation between the sender and the, as we call them, Alice and Bob, because in an entanglement, there is no sender receiver, there are two parties. So this is, of course, as you said, practical problem that it solves is, of course, that our way of generating randomness can be done on a very small portion of an optical table going forward, maybe even in a little box. And so this brings in a great, practicality to this DI-RNG, community, which otherwise is, of course, a little bit limited because of these distances. I mean, one of the things which happened, there was this very nice paper on superconducting qubits that was done by a group in Europe, but then they had to actually build a tunnel which was 30 meters long to separate two dilution refrigerators and try and show a somewhat loophole-free experiment with superconducting qubits. So you see that there is a lot of infrastructural and operational challenges on doing this sort of randomness generation using loophole-free architectures in the Bell scenario. Did I answer your question? Because I can't see you.
Answer it, of course. Partly the other thing I wanted to ask, maybe I'll later.
Please.
But let's move on to Srivati.
Yes, please.
Nice talk, Urvashi.
Thank you, Shivashita.
So maybe similar question which Archunda asked. So if I want to compare like the length of the randomness which is produced typically in Bell scenario and in this LGI scenario, is there a way of comparing this?
Yeah. So I mean, of course, the length of the random bits is what you're talking about. And so this length of the random bits, I had just one fraction of a second. So, the slide that I showed you, which had that information, which is the length of the random bits. So in our experiment that we have done, at the moment, we have 1 million bits simply because you see our source is a photon source where we did not really pay any attention to the generation rate. It was essentially this one, right? So as you can see, number of bits, right? The first experiment that was done in the Bell had 42 bits, okay, in the Pironio et al. Paper. And then it went on to 1024 bits. And then, of course, there are others. And then they went on to 10 to the 7, 10 to the 8, and so on. So in our case, we are at 1 million. But then that is simply because we have a photon source which is generating, photons at a certain rate. So, I mean, of course, the length of the bits is proportional to the length of the generation of the photons in this case. So if I have a much brighter source, which of course I can definitely have, which we do have in the lab as well, and there are others who have it as well. So if I use a gigahertz rate source, then my length will just proportionately go up.
But if
length is not a big concern. What is a concern would be, when I do extraction and amplification, how much random bits will remain. That is the problem we are currently working on.
Exactly. So if you use bright light source, it may give you better length, but
not bright light of any kind, but bright single photon source.
Right. Okay.
Yeah. Yeah, but then, I would wait to make the final comment, because once we do the expansion and extraction, then we will lose some bits as well. So we will see, how they would compare. But then currently the length is a matter of photon source brightness in our case. Yeah.
Okay, thank you.
Yeah, thank you.
Thank you, Urvashi.
Thank you very much.
Due to time constraints, we can't have questions now. But I hope you'll agree that during our coffee break, that is from 4 to 4:30, some people may ask you questions that they may write to you. So please
Oh, sure. I'll be online then.
Yeah. Computer on your email if somebody asks you.
Do you want me to be on the Zoom link or check email?
No, not Zoom Meet. You can be at email. Check your email from.
Sure. Absolutely. And apologies once again for the.
You can give an insight.
Yeah.
So again, let's thank Urvashi
once again
for the very nice talk. And let us move on to the next speaker. And we are very happy to have Professor Prashanta Panigrahi with us here today in physical mode. And Professor Panigrahi, as most of you know, he was at ISQIC Kolkata for a long time. And now he's at SOA University.
Yeah, okay. Yeah. Thank you, Pankaj and the organizers for giving me this chance. And of course, thanks, Archon. So I'll be talking about light, but in a very simple thing. This double slit experiment is the one which we are familiar. We have been taught, and it has been there in the books in the time of Dirac. So I have seen many people starting their talks with single photon, can it interfere with itself, from Dirac's book. So this is a multi-slit analog of that, and discrimination of states is something slightly different, which may come up, but right now I'll concentrate on this multi-slit interference. And I would say that my motivation for this work was Tabish Qureshi's talks in many of our workshops, where you are pointing out some very beautiful quantities which are related in multi-slit experiment. Particularly, there was an experiment 2001 in physical vectors where they looked at 3-slit experiment. And quite amazingly, if you see the abstract, they found out that if you put some obstacle in front of one slit, the visibility increases. Imagine 3-slit experiment, and we are putting some bad object in front of the third slit, and the visibility of the pattern improves. So that was my curiosity, that how it happens. And the whole thing started during COVID period, and actually the students who were going for their PhD are the ones who worked out these things. And okay, so this is the multi-slit experience, and you will find out that this quantum coherence, quantum entanglement, and which path information comes in. What was the surprise was the this quantum entanglement. It came in, and visibility, which is measure of coherence, you would expect, because double slit experiment, the visibility naturally appears. Which path debate has been going on. On this one, it's okay. I think it's readable. It's readable. Okay, so what I'm trying to say is that visibility is something which we are familiar, because starting from Young's double slit experiment, we know that fringe visibility has been there. Now, after Dirac's book, and during the foundation of quantum mechanics, which path information played a very crucial role. because wave particle duality came through that. So many of you must have heard the moment we try to see which path light is coming in, photon is coming in, particularly when it is single photon, then there is particle nature is emphasized, no interference. Only when you don't know which path it comes in, then the wave nature comes in. Wave particle duality has the information coming from which slit it is coming through, which path. But as you will see, this quantum entanglement comes in a very funny way, and it's a very nice identity. There's the exact reality relation which connects these three, and you can derive it as a complete mathematical identity. And what was nice was that this is what I've described as an experiment, nature photonics experiment, which was reported in February 12, which exactly verified this. That was the motivation to give this talk here. So you see here, these are the kind of why am I not coming here? Okay, anyway, you see the standard double slit experiment. Plane wave is coming in, and there's interference pattern, and you see minima and maxima. So as we all know, now wave particle duality and wave phenomena which comes out there. Okay, so if you would sort of follow standard quantum mechanics, you can see that the psi1 star psi2 plus psi1 psi2 star, the interference that is responsible for visibility, and the coherence of plate has been defined slightly differently, but is related to this. For example, this L1 norm of coherence, which came up in 2013 and 14, is related to that. But this is a good old visibility which comes in interference experiment, and you can properly normalize it, so it will go from 0 to 1. This is the okay. Now, for example, so how do you sort of can give a very nice density matrix type of formalism to describe it. Let's not get into the mathematics too much. All I'm trying to show is that you can actually deal it with like a density matrix. So this is a standard introduction. Some of you people are all familiar with it. So the coherence lives in the off-diagonal element, and the diagonal fellows have information about intensity and visibility. Okay. So basically, I want to point out that visibility and the path, which fringe it or which slit it goes through, they're related, and the off-diagonal element that brings in coherence. And if you together look it in the form of a density matrix, you'll find out entanglement has to necessarily come in, and that entanglement is the entanglement between which path. Okay. Okay. So now, for example, this is the motivation I was pointing out, that it very mathematically and in a very nice manner. The whole thing started in 79 when Jurek and Utos asked this question, that how do you really quantify it? They came up with this path predictability called P, and visibility defined the standard way, I max minus I mean by I max plus I mean. They found out there's a very nice identity, duality relationship, P square plus B square is less than equal to 1. So this is the kind of debate which has been going on since Einstein, Bohr, and those kind of things, that wave particle duality. So that was mathematically formulated by very nicely in 79. And since then, it has been in the radar. For example, Greenberger and Yassin. The Greenberger was looking at it when I was a graduate student for some years in City College, 1982 onward. And this was the paper, 1988. They also analyzed it. They defined something called D, path predictability. So there were again this kind of two-term relationship, this P square plus mu square less than equal to 1, B square plus B square less than equal to 1, those kind of things are there. So now, so there was this beautiful experiment I was referring to, you see, which was using atomic beams. And so if you see, there is this atomic quantum state loses information with photon scattering, which path information is carried away by the photon field. So there they point out that in certain cases, the fringe becomes better visible. That is what really was very surprising. This was the experiment. Okay. Okay, this I think it can be made as a small one. It's okay because I'm just trying to give a gist. It's fine. Go back. Yeah. So this experiment, as I mentioned to you, that in a triple slit experiment, that the visibility increased, and that increase was manipulation through which path information led us to our work. And this is the published work, that there is an exact triality relationship between coherence, path predictability, namely which slit it is coming through, and this entanglement as measured through eye concurrence. And this triality was verified. I think I have hopefully quoted that paper, like the Nature paper, photonics paper, February 2012, which actually verified this one. I may give you that reference later. So this visibility and path predictability you are familiar. So eye concurrence is a measure of entanglement, which actually has a very beautiful geometry interpretation. I'll tell you at the end. You will show that the entanglement actually is an area between vectors. Suppose you have this Alice and Bob kind of scenario. In fact, you can show that a post measurement. If you take a Bell state, if you carry out a measurement at the end of Alice, post measurement vectors at the end of Bob, if you can measure the area between them, if it is Bell state, area between them will be maximum. If it is separable state, area will be zero. So entanglement as an area, we had shown earlier. This is work with my project student, Vinil Bhaskaran. That identity was very useful here because that led to the so-called eye concurrence. The area between vectors nicely manifested here, and that led to this exact identity. Okay, so let me just go through the history. This is Greenberger and Yassin. For example, you have to slightly change the definition. Earlier, visibility was Imax minus Imean by Imax plus Imean. So you have to slightly, take when you take n particles, you have to slightly change it. See, for example, it is related to off-diagonal elements, rho ij mod square. If you see recent L1 norm, it is rho ij mod. You have to take rho ij mod square, slightly normalize it 10 to 10 minus 1, so that it nicely will match all the identities derived so far and goes to visibility when n is equal to 2. So it's called the Hilbert-Smith coherence. Okay, so it's just a definition in terms of off-diagonal elements, as expected. So now in the general case, for example, you have to put a path detector. So that is the one which will tell you which path. That essentially will involve diagonal elements. So if you see, if there is a row 1, 1, row 2, 2, row 3, 3, they are like diagonal elements. Their difference will tell you if there is one path which is more preferable as compared to others. So that will involve diagonal elements. So now, you can sort of nicely manipulate it. Equation 8, you will see the real part is there in rho ij, and the basis function is I j psi k, that is our electric field or atomic beam wave function, whatever you may say. The phase is exponential part, and you have put now detectors. So detector will tell you which path it is coming through, dj dk. This is made artificially, so that's the reason you have rho prime. So now if this path detector, which will essentially bring in this entanglement between paths, if they are orthogonal, then you know that you exactly know which path it is going through, then there would be what happened? Then there would be obviously no interference. But if they are not orthogonal, namely not delta jk, then you don't know which path it is coming through, and then you will see all the effects will nicely manifest. So this thing will be introduced, and finally you sort of integrate them out. You see dj dk, initially outer product was there. Now you have integrated out, but in the process, the j and k indices are associated with the state j and k. So they're keeping track of the state. So this is how von Neumann measurements are carried out. We followed exactly the same description. Okay. So, and in the process, we have used this language called quantum, which I learned from Tabis. So now you have to sort of slightly redefine things. The moment this decay dj is there, you see that non-orthogonality, if it is orthogonal, of course, it is delta jk, it will go back to nu what you know, namely the visibility measure of diagonal elements. If it is not orthogonal, then you have the decay dj element coming in here, which basically tells you is the the outcome of the measurement. So if it is non-orthogonal, both the paths are present. So that you have to bring it in. Measurement has to come in. So then subsequently, I will just tell you, because of this time constraint, that manipulation is absolutely, simple manipulation. You look at the mod square because you are looking at interference, and for example, equation 11 shows you the standard cosine factor that comes in, which is responsible for interference. And same kind of things here, except that you have to do a little bit of work here. So for example, this off-diagonal elements, you can convert it into amplitude intensity fluctuation, so that will get related to that. And and then this nu square would be related to with that. So you have to average over the angle theta, because when you are observing at some point, photon is coming from all paths. So these are things which you follow what the experimentalists do. And then finally, this average quantity, and again you have to keep sort of massaging it, so that you see, for example, now you come back to this path generalized predictability. As I told you, it will involve diagonal element, because it will tell you that which slit is more weighted. If one of them is the probability of getting more, then the asymmetry can come in. So that main point to note that it involves diagonal elements, rho I, rho jj. So then you have to define it so that you go back to the original identities. That is your normalization condition. For example, if rho jj is equal to 0, then you come back, for one path for certainty, p becomes 1. So like those kind of normalizations you have to use. If all paths are equal probable, then rho ij is equal to 1 by n. Then you see this predictability becomes 0. So using that normalization, you came up with this thing, rho I square 1 minus 1. So these are like your checking conditions. P is equal to 1 and P is equal to 0. So that fixes for you equation 14. Once that is done, that involves diagonal fellows. You can see, and you can see that it is the difference. Rho 1 minus rho 2 in the simplest case will tell you what is this P. So anyway, these are all simple manipulations. Let me now go back and so then D, if you remember the quantity D, which was introduced in this later on, this is path distinguishability, with the detector is associated. You see Di, Dj comes in. You have to differentiate that thing. So it has, you see, both diagonal fellows and off diagonal Dij also, because it will see the difference between which path it is coming through. So if it is delta ij, then it is completely diagonal. You see, it is a mixture of diagonal, which has information, and the entanglement comes to this route. That I wanted to emphasize. So to see the visibility is completely off diagonal element, P is a diagonal element, and this object D, which is path distinguishability, is a mixture of these two, and that is the key. So you see, now D square go back, and then this definition is there, containing both ij and iijj weight factors. All right. So now it is more of algebra, and this is just to emphasize that when di dj is delta ij, then only one path is there. These the paths are distinguishable. D is equal to 1, others go away. So basically, you sort of try to fix your boundary conditions. When it is 1 and 1 is equal to when it is 0. So accordingly, you come up with your expressions with suitable normalizations, just like you did it for P, so that your quantities are properly defined. Then you go back and check that D square plus nu square is equal to 1, which was earlier derived by Greenberger and Assin. That also follows. This is just for normalization purpose. But main point is this, that visibility, good old visibility, which is the off diagonal element, difference between diagonal elements, which tells you which slit it is more favored, and a combination of diagonal and off diagonal elements, which comes through path distinguishability through this Bornemann prescription of measurement, plays the key role. So once all those quantities are properly defined, then you go back and sort of modify the whole thing, and you will find out this di dj will not appear explicitly, but so they will be there hidden in these things. So I will not put any more mathematics. All you do is you sort of suitably p square plus nu square is equal to 1 minus some object. That object, if you put suitable conditions on dij, then you will find out that it will become this additional quantity which is entanglement. So that needs some amount of steps, but pretty straightforward. All that you have to do is completeness of measurement, and these measurements are POVM type of measurement. So there is nothing more than that. So once you assume those things, so these are all pure mathematics, and you can see very nicely it comes out precisely as this entanglement E square, which is basically concurrence. And to our good luck, we could recognize that it is entanglement, because this is exactly the measure we had actually obtained during in concurrence with the area between two vectors, which is our earlier work. I'll show you the reference. Once that became clear, this these three-term recurrence relation followed, triality relation, namely which path, visibility, and entanglement square is equal to 1. And entanglement comes in a necessary way because of this path entanglement. You can actually use this expression equation 26 to sort of show that how the paths are entangled. Okay, so now, as I told you that this is the work which I was referring to, that when you so this one you can actually this is an example of two particles which has been generalized to n particle also in this paper. So essentially, you go to an Alice Bob kind of scenario. You at Alice side you measure, consider Bell state 0 0 plus 1 1 by root 2. If Alice is measuring 0, Bob's vector would be 0. If Alice is 1, Bob's would be also 1. Now you can see 0 and 1 are orthogonal. This you can show in a general way, that looking at it from a measurement perspective at Ali's side and post measurement vectors on Bob's side, that area between those post measurement vectors will precisely give you the measure of entanglement. This we have shown for n particles, and it beautifully matches with the I concurrence, which was obtained by Rungta, Case, and et al. In 2001. And interestingly, while proving this, we needed a triangle inequality, which we call as Lagrange inequality. But this referee pointed out that this inequality was due to Brahmagupta. So this he derived it apparently in the context of a triangle. So this Brahmagupta and Lagrange inequality played a very key role in deriving this result. And then, okay. Now, so that was, so as I told you, the state discrimination followed a key, the DI, DJ, that are non-orthogonality. State discrimination played a key role in our thing. So this, in the morning hours before lunch, Alok was pointing about ancillary state being used to check the, the correlations in the state, namely the maximal entangled or not, through ancillary measurement, namely, this Hadamard control operations, Hadamard kind of thing, revealing information about phase and bit. So I would like to point out that this kind of thing, which was useful in our previous calculation also, we had written this paper, and fortunately, Professor Anil Kumar, who is over there, verified it experimentally using an NMR. Namely, you can actually check a state entangled or not without destroying it. So this kind of thing, measurement plays a very key role. And recently, we had written a review in honor of Professor Anil Kumar. So I think I'll stop here. What happened? Okay, I'll stop here. Okay.
Thank you, Professor Panigrahi. Now we can have some questions. Again, let me do the same thing by the time you come up with some questions. Or should we, yeah, I'll give it to you. So let me ask the question. So entanglement actually, introduces a new element into this complementarity relation.
Yeah, yeah.
Which was earlier formulated for visibility versus this
path distinguishability.
So how do we physically, is there a way of getting more physical insight? I mean, what role entanglement plays here? Does it?
See, for example, okay. See, if you really look in terms of coherence, that is pretty clear. The off diagonal elements, that part is coherence, that is unique. Now, this diagonal difference, which is again, there was earlier this thing was hiding because the D and P difference they are not able to see. This off diagonal element difference, that if you quantify properly, the remaining thing has a information about which path, how the paths are entangled. As you know, for example, PO people work also this path entanglement that can be useful as a resource. If the path, you can actually use it for probing purpose. You can use just like in a physical evaluator experiment. It's so that you put some obstacles here, the visibility increases there. So in principle, it could be useful for sensing. So the use of precise quantification and use of path entanglement will come in once you define your visibility. And if you see, it has a beautiful group theoretic interpretation. For example, 3 sheet we have worked out in terms of SU3. you precisely do that, in terms of German matrices, you find out that that difference exactly comes out in this way. So that basic quantification is the one thing we are missing between D and P. Yeah, yeah, yeah.
Sir, I have two questions. I'll be brief. First question, your generalized concurrence measure is can it be used for mixed states? And the second question is, have you devised any measure for higher dimensional systems such as Q-treat?
Yeah, in fact, mixed state paper, Shreya and me, we are co-authors. It is the Journal of Physics A. You can actually do it for mixed state. But I must say the geometry becomes very complicated. So we have not, apart from that first paper, we have not done much after that. So we can do it for mixed state. And, for Q-treat, in fact, one of the co-authors, Samik Mahanti, and this other guy who is in Calgary, they are all isopropyl rules. They have done it for Q-treat. I'll give you, it's published actually, with a script, I'll give you that reference. Yeah.
Thank you, sir.
So there also, it very beautifully comes out in terms of volume and area also. See, essentially what happens is that if you take Bell state, for example, but generalized two particle state, if you measure early side, choose the basis 0 and 1, the bob side vector would be some two vectors. What the area between them exactly gives you the constant. And the same thing generalizes. And Q-treat also, instead of area, sometimes it can become volume also. So these people did it. They have the energy to work out the volume, area, and all those things. So Samik Mahanti is one of the authors. Yeah. Q-treat. Yeah, sure. I agree.
Let us thank the speaker once again. So we move on to the next talk, which is online. And so there.
There we go. Hello.
Yeah, hello. So you are audible, and you could also please start sharing the slide. We can see
Yes,
there.
yeah, I'll try that. Here we go. Oops. Okay.
Yeah, fantastic. So let me now, formally make a very brief introduction. Professor Andreas Winter needs no introduction. He's, one of the founding figures of this area, quantum information, many, mathematical formulations, etc. He's at the Autonomous University of Barcelona. So he will be today speaking on hidden Markov models, classical quantum and VR. And Andreas, you have 30 minutes.
Okay, great.
Please, welcome.
Okay, thank you very much for the nice introduction. Let me just minimize the... Okay, so I cannot get rid of well, okay, never mind. We'll manage. I wanted to get rid of the side panel, but I guess you don't see that. No, you must see the actual slides. Yeah, so I want to talk about relatively recent work. I mean, as you see in the bottom line, actually, let me go out of this. I think this is the wrong application.
Sorry, Andrew, if I disturb you for a while, your voice is not loud enough. So,
I see.
Can we fix it from here, or do you need to turn on your volume from there?
Well, okay. I mean, let's. I'm unmuted. No, let me just go out of this here because actually I need to open another. I need to open this presentation PDF. I'm sorry. Okay, I didn't because I didn't have the pointer. I'm sorry.
Yeah. You managed to fix it in one of the earlier talks, day before yesterday.
Yeah.
Use the volume from here. So you can try doing from our end also.
Okay. So yeah, can you hear me a little bit better? No? Okay.
Almost the same, I think.
Okay, let's see. Now I'm sharing. Okay, this should be it. Yeah, this is much better. And now full screen. So, how's the sound? Is it any better? No? Okay. Now I don't hear it all anymore. Okay. Yeah, you're very low too, actually. I don't know what's going on.
It's coming from the speaker. So can you turn the volume up of the speaker? Turn it to maximum.
Well, my speaker is up, but I mean, there's a problem with the microphone, I guess. Do you have a problem with the mic?
Well, I think, yeah, is it audible or people can move forward?
Okay.
Yeah, yeah.
I really don't know.
If not audible, it would have been better. I mean, nicer if it was more
Yeah,
loud.
okay.
Let us go ahead with the talk. We can
Yeah.
hear you.
Oh. Okay. I suppose I have to check in Zoom. What is the? It should take. I mean, there's the audio speaker. Okay, that's the issue. Okay. Well, okay. No, the microphone is there. I mean, like it's picking up normally, but I can shout a little bit more.
This is
Okay.
nice enough. Now it is better.
Let me see. Okay. Now here's the thing. Okay, better. I can turn in the input volume. Okay, great. Good. I think that's it. So again, I want to talk about work that is relatively recent. So the paper was published last year. The preprint is already a while ago with Marco Fanizza and José Lumbreras. But actually, the ideas, they go back to a much older work with Alex Monraz from, it's like 10 years ago now. So we left some unfinished business and we kind of went back to it. So what I'm talking about, I mean, despite the maybe confusing and mysterious title, is finitely correlated states. So, or I mean, many people know this as matrix product states or matrix product operators. So what I mean by this is ideally the infinitely long, a state of the infinitely long translation invariant chain. And they are generated in this way that you have like a sort of an initial state omega, and you have some maps that output something. Those are the spins you get, and they have some memory that is passed on infinitely. And so what I show in this picture with this tensor network is just a finite chunk of the chain, because we never actually treat directly the infinitely long chain. We always talk about the sequence of n-side reduced states. And yeah, like I said, so if D here is actually an isometry of Hilbert spaces, then this is what is known a matrix product state. And you have conditions on omega here in this map D so that you get actually a translation invariant state. So to be precise, in the language of Farnes, Nachtigall, and Werner down here, who introduced this language of finitely correlated state, this is called a C star finitely correlated state, so maybe you could call it a quantum finitely correlated state, because this map D here maps actually quantum systems. This H is an internal memory that we don't observe directly, and U is the spin that is on which the actual state lives. And in the paper, they also considered general finitely correlated states where we do away with the Hilbert space structure, at least one of them. I mean, obviously, we still want to have a state here, this green thing that should be down here, that should be a state. But D is now just a map between a linear space V, so is a vector space V, to V tensor product, the matrices over U. And pi, well, I renamed it from omega. The omega was a state. Pi is now just an element of this vector space with a certain fixed point property so that we get a density matrix here. And so that's what they call a finitely correlated state. But already in the paper, they asked this question, so what does this added generality actually do beyond C star finitely correlated states? So in fact, they asked the question whether there are finitely correlated states which are not finitely correlated in this more intuitive sense that we have here, of a quantum system that's evolving and in each time step outputting another quantum system U. So for the rest of the talk, I will actually focus on very specific kind of finitely correlated state, namely what we would call a classical finitely correlated state. So the state is actually a probability distribution on infinitely long sequences with a translation invariance property. So what we can think of this as observation of a like in principle infinite time series that is translation invariant for, well, to make the whole thing accessible by finite means, let's say. And these UT are just letters from a finite set. So we just observe some experiments. Yeah, I'm stressing a lot the stationarity, but this is like, for me, this is more a mathematical convenience, which goes back to Farnes, Nachtigall, and Werner. You can do certain things without this, but like I said, what it makes is that a finitely correlated state can actually be defined by finite means and also observed by in finite time. Yeah, so I just want to repeat, even though the chain is infinitely long and the probability distribution is defined on infinitely long words, the distribution is completely defined by the marginals of the finitely long words, which are kind of just distributions on a finite set. So that's very nice and intuitive. But it's like why this is the case, that's basically Kolmogorov probability theory. And so the way we thought about this is in terms of an of this process that generates the finitely correlated state. We think of this as like kind of basically the explanation of this. So the process itself, it has correlations, and sometimes it's very easy to come up with examples where the correlations are actually infinitely long. They last forever. But in some sense, there's a finite aspect to it and a finite correlation. And we think of these tensors here as like a hidden cause. So where we only observe the u's, the u0, u1, etc., into infinity, but there is some kind of process going on behind the scenes, a hidden cause that generates that. And so obviously to talk about this in proper terms, we have to specify the nature of this causation, just like I did before for the finitely correlated state. So let's go back to this. Oh yeah, before we go there, here's an example from a potential lab experiment. I think this is from Serge Haroche's Nobel Prize speech. So all of this hidden stuff is here. So there's a kind of a source that creates atoms or ions in a particular state. So ideally, they're all created in the same way. Then they undergo certain potential preparations, and then they enter the memory system. Here, this cavity has interacted before with similar atoms. It keeps a correlation with them. Each new atom interacts with the cavity, with the field, and comes out and can be then observed. And so this observation here in D, the detector, those are the U's that we can observe in our process. And so one of the questions that we asked ourselves was, well, can we, for example, infer the quantum nature of this internal mechanism by observing only the distribution P? Now, it's a bit of a foundational question. You can also put it as an inference question. So like just observing this process, can you learn something about the physical nature of the hidden causation, of the hidden process that generates it? And so the rest of the talk are these points 1, 2, and 3. So I want to talk about these different kinds of causation. They are characterized by different types of memory. And then I have to talk a little bit about sort of mathematical background, but hopefully I will try to pass that very quickly and have to refer you to the paper because obviously I don't have that much time. And so then like the last part is the spoiler. I have to have that because I might run out of time, which shows that indeed a classical memory is in a certain sense strictly weaker than a quantum memory, and that in turn is strictly weaker than the general finitely correlated state process of Farnes, Nachtigall, and Werner, in the sense that there are processes which can be characterized by something here on the right, like this, what is called GPT here, but not by a quantum memory. And there are processes which can be generated with a finite quantum memory, but not with a finite classical memory. Okay, so let's see how I move the time. So it's not too bad. So yeah, the easiest one is the classical memory, because after all, we have a classical process, and those things are called hidden Markov models since ages. I mean, you know what is a Markov process? That is an infinite time series where each observation only depends stochastically on the latest one, not on the entire past. So what it means is that the conditional distribution of each observation ut would, well, sorry, I'm talking about the x's here. Each xt, the distribution of xt depends on xt minus 1, but not anymore on the previous ones, right? I mean, the conditional distribution of each xt given the entire past actually only depends on xt minus 1. That's a Markov process, and a hidden Markov model, that's in simple terms just a function of that. And so a little bit more in keeping with these tensors that I wrote before, the way it goes like this. So these x's are now also finite observations. They come from some finite set. And D is just a stochastic matrix. This tensor T here, this maps x, a past x to a future x, and a future, a present output. And it's just a stochastic map. That's kind of, I mean, that's when you think about it a little bit, this is equivalent, I mean, what the kind of processes you get when you observe the use, that is equivalent to saying, oh, this use is just a function of a Markov process. And so, introducing a bit of notation, you can write the probability law, by which I mean the probability of a finite string of observations, in this very simple way. So basically, just you have to know a state here that goes in, a distribution. You have to evolve it over some steps with the maps that correspond to outputting precisely U1, U2 up to UL, and then you have to, at the end, contract it with the all-1 vector. Yeah, so the all-1 vector in probability is important. It's like the identity matrix that represents the unit, for which we need to say that something is a probability distribution. Okay, so there is this kind of tensor contraction formula to express the probability law. And that's called, I mean, like this kind of whole thing would be called a hidden Markov model. And the way, like in the green box, a way of writing the probability law in this particular way of product of matrices. So these du are substochastic matrices such that their sum is a stochastic map. And stochastic map means that the d bar acting on the all ones vector leaves it invariant, and if we activate on the d bar from the left from the other side on a probability this vector, then it also leaves that invariant. That's the pi here. And so, depending on the context, this has all sorts of different names. So, in particular, for example, it's called positive realization. And so, yeah, more interestingly for this audience is the quantum memory case. So we call this a hidden quantum Markov model. And so the difference would be that those x's now are not just letters from an alphabet, but they are states on a quantum system. And this quantum system, I call it H, the Hilbert space, and S of H is the set of states. And D is what we would call a completely positive instrument. So I mean, I hope you've heard of this kind of language that goes back to the 70s, I think the work of Lewis and Evans. So an instrument is kind of a generalization of a completely positive map of dynamics. It includes dynamics and measurements. And so like for our purposes, it's basically just a collection of completely positive maps du, such that their sum is a completely positive channel. So it has to be actually in our notation, it has to be unit preserving, because it's basically like the Heisenberg picture, and it has to have a stationary state. So like again, we have to have the d bar leaves the unit invariant, and if we act on the one side, and if we act on the other side with a linear function, which is the stationary state, we also leave that invariant. And again, we get the same kind of formally of the probability law. It's this tensor contraction. And this is now called a completely positive realization. I think that we introduced that in the paper with Monraz. Yeah, so this is basically just a handy way of seeing the similarity with the quantum case, but with the classical case. But of course, I mean, I guess the picture is even more convincing because all it says is, well, okay, this D just has to evolve the internal state, which is now a quantum state. So obviously, we need a completely positive map. And yeah, so this is in the language of Farnes, Nachtigall, and Werner. This is a C-star finally correlated state. And so, in particular, this kind of experiment that would be in principle described by such a thing, at least if Harosh sets it up in such a way that the internal memory has reached a stationary state. So, for example, you might think that maybe after starting the experiment, we just let the internal memory we just wait long enough until it relaxes to the stationary state. Typically, it's unique, but even though it's not always, of course. And so here is what happens when you have a general linear structure. So this is kind of, you simply forget the fact that you had probability vectors or states evolving in this yellow sequence. But these are just elements of a vector space. Because in the end, like to make this formula here at the bottom work, what you need is that you have linear maps with certain fixed point properties. You need a fixed point from the right and from the left of the sum of those DUs. And these DUs otherwise are just linear maps. Tau is an element from the vector space and pi is an element from the dual. So in other words, it's a linear function. So that's kind of how the Heisenberg people in this world think about states. It's a linear function on observables. And so, yeah, formally you have the same kind of rule here, down here. You just act with a sequence of those maps, one after the other on the unit, and then you contract it with this linear function pi, which I would call a state now. And of course, you need some kind of normalization. Also, pi of tau should be 1. So this is basically, that's the trace condition, that the trace of a state is 1. As I'm just abstracting away from this, I'm forgetting that for a quantum model, I need actually matrices and positive semi-definiteness. I just say, well, okay, I'm just keeping this linear structure. And so because V is a real vector space, I mean, that at least makes sure that this value P down here in the last line is a real number. There is a problem with these so-called quasi-realizations. I think this is a word that comes from the hidden Markov model theory from the 1960s. So we had positive, completely positive, and now quasi-realization. And so this would be a general finitely correlated state in the language of Farnes, Nachtigall, and Werner. So a problem with that is, unlike the classical and quantum case, where we built it in a particular way, when I just talk about the linear vector space and linear maps like this here, there is no a priori guarantee that P of U is actually positive. So, I mean, what I would need to actually interpret those numbers in the green box as a probability. Yeah, what I get is from this normalization here, from this pi of tau equal to 1, I get that the sum of the p's, if I sum of the whole all sequences, I get 1. But there's no a priori reason why they should be non-negative. And in fact, there's a reason for this reason, for this absence of reason. Sorry, it's because the checking this positivity is undecidable. So in the sense that as a mathematical problem, if you're given the vector space tau, pi, and those maps du, question is P of U underscore, which is a typical string here, is that positive or 0 or not for all lengths of strings? That is undecidable in the Turing sense. So there is actually no good answer to this. You have to hope for the best in some sense, but we'll come back to this in a bit, in a short bit, because I don't have that much time. So here are some simple examples. I said already, like if you have a Markov chain, that would be an example. So even simpler, if you have just independent, identically distributed observations, so that the probability law is simply the infinitely repeated P1, the single letter distribution. That, when you think about it, requires no, or rather trivial memory. So you need a dimension of this vector space equal to 1. You don't need to distinguish any states. You don't need to actually memorize anything. Slightly more complicated is so-called definitive distributions. So those are called definitive because Definetti introduced them as the unique permutation invariant distributions on an infinite set of observations. So these they are convex combinations of the first type of these IID ones, where you have we basically have a probability distribution of a p-x's, each with a pi x, and if it's x, then you have this infinitely repeated px. So the interesting thing about these px infinitely repeated is that they are mutually orthogonal. I mean, each of them is ideally distinguishable from the other. If you have infinitely many observations, they are perfectly distinguishable. And so you can realize such a distribution with a memory that simply memorizes this x here forever, from the beginning to the end of time. And indeed, that of course requires a memory that is equal to the size of this set x here. And indeed, you can convince yourself, because of this distinguishability of the IID distributions, that is also necessary for any quasi-realization, I mean, as a dimension of V. And so, yeah, in particular, you can easily come up with examples which are stationary processes, but which are not realized as hidden Markov models, hidden quantum Markov models, or even quasi-realizations. Namely, if this alphabet size here, if this set in this convex combination is genuinely infinite, and all of those probabilities are positive. Yeah, because, I mean, by this reasoning we had in the second point, you need infinite memory to represent this process exactly. So here's an example that is more quantum, that comes from the paper with Monraz. Our vector space, it looks like qubits. Our vector space is simply the 2x2 density matrices. Actually, it's only the self-adjoint part of this 2x2 matrices. Tau is the identity as we want in quantum, and pi is simply the maximally mixed state. And we have the following maps. So the first two, they together make a projective measurement, right? We're projecting onto 0 and 1, which is like, I don't know, z 0 and 1. And dx and dz are also two maps, but they are simply with certain probability rotations around x and z axis in the Bloch sphere. And the last one is the transpose, which of course is not completely positive, but it's a perfectly well-defined map on this vector space. And so you can think of, like I want you to think about this briefly, when alpha and beta are irrational multiples of pi, then the dynamics ends up exploring the entire Bloch sphere densely. I mean, obviously, if you start from somewhere, let's say in the 0 state, you can only go to countably many different states after some amount of steps. But the set of states that you reach, they are all on the sphere, and they cover the sphere densely. Okay, so if we remove the last map, then we get actually a hidden quantum Markov model with a qubit memory, because we don't need a transpose. So of course, I couldn't use that because I need a completely positive map. But actually, if I want the last map as well, is dt, I can do that with a four-dimensional, with a quasi-realization. Actually, sorry, with a completely positive realization with the four-dimensional Hilbert space. But okay, that's I always each time I give the talk, I realize it's more confusing than is necessary. So let's remove the transpose and look only at the others. So let's not talk about the recovery of the internal mechanism, because it's like an algorithmic problem. It's related to self-consistent tomography. There's a beautiful series of paper by Bloom cohort and collaborators, but I don't want to go into this. So let's go back to this question: what guarantees positivity? Yeah, so we have those maps du. By concatenation, we get maps du bar, where u bar is a generic string. And when we reflect on this, how do we know that in classical quantum we have positivity? Well, it's because our internal memory is already built on some operational theory. So abstractly, this is an ordering. So in probability theory, we have an ordering because we have probability vectors who have non-negative entries, and stochastic maps preserve this property. And we have, in quantum case, we have positive semi-definite matrices, which are states, and the completely positive maps, they preserve this property. And so the general answer, what guarantees positivity of this quasi-realization is this here. We have to have a convex cone in this vector space V and another cone inside the dual cone in the dual vector space, such that tau is in this cone C, pi, this dual object is in the other cone C tilde, and the cones are preserved by these transformations. So the du acting on this cone C maps us back into the cone C, and du acting on the other side on the dual cone acts us back in the C tilde, acts us back into C tilde. If that is the case, then necessarily P of u is positive for 0. And that's basically because the dual cone encodes that. The dual cone is precisely all the linear functions on vector space V, which are non-negative on every point of the cone C. So like this is, I mean, there's another computation question. Given the cone C, can you actually compute C tilde, C prime? Again, this is a difficult one in general, but we assume that we know these cones. And so the magic is that this is actually necessary and sufficient. If the probability law is actually genuine, if this P of u is always non-negative, then such cones exist. In fact, there is a smallest possible one and the biggest possible one, which are essentially obtained by evolving the unit through the maps du infinitely many times and also evolving the state pi through this du's infinitely many times. So these sets are countable here. They span a cone, and then we have to take the closure. Those are the smallest and the largest cones that we can use to justify why those maps actually give a probability law. So in general, those cones are not unique. Like here, I said I could take C equal to the minimal cone and C tilde to be the dual of the maximal cone. But I could also simply take C tilde to be the dual of the minimal cone. So in general, there are different so-called suitable cones, but okay, this is from the undecidability we know that it's going to be difficult in general to even find it. And so I just want to talk briefly about the interpretation of this. So if we have a finite dimensional quasi-realization of a genuine probability law P, what the explanation is, the hidden causation, is actually the dynamics of a so-called general probabilistic theory. So those are given, I mean, like I'm abbreviating the history, so this starts with Gunther Ludwig in the 60s. You need a pointed and generating cone C of the vector space, so that the dual cone is also pointed and generating. Tau is a unit, this has to be in the interior of C. S is the state space. This is the set of all linear functions that are positive, so they're in the dual cone, and also evaluate to 1 on the unit. And so this is kind of abstracting away from quantum mechanics. And the measurements are given by the effects, which are all the elements in the cone C, which are, so these are positive elements, so to speak, in this vector space V, which are less than tau, less than the unit. And using that, you can write even the evolution. So ft is the internal state at time t, and if it is hit with a map du, which should be inside the box here, the process outputs the measurement result u, and the internal evolution gives us a state ft plus 1, which is given by this law here in turquoise. Yeah, so we have to renormalize with a conditional probability, and then we get another state. Okay, so I don't think I have a lot of time for this reconstruction, but maybe I will just talk about this thing very briefly if we have a quasi-realization of no, sorry, maybe okay, let's leave that. I mean, actually, this is why those things are called finitely correlated states. So this has to do with a certain infinite size matrix. We have to arrange the probability law into a matrix indexed by rows and columns given by the words over those u bar and v bar, and then the finite dimensionality of the quasi-realization it translates directly into the rank of this matrix. So this matrix somehow carries all the information about the quasi-realization. And so in particular, if P has a positive realization with S internal states, then this dimension is at most D. And if you have a completely positive realization with a Hilbert space dimension T, then the matrix spaces T by T matrices are T squared. And so the dimension here will be at most T squared. And so one of the questions is that you can ask, which people in the 60s asked themselves, so if you have a finitely correlated states, is that actually also a sufficient condition for having a classical hidden Markov model? And so okay, let's jump over this here. So we have to assume that we have this finite dimensional quasi-realization, which is actually the finite rank of this infinite matrix. And so this was famously answered in the negative, this question I just phrased, by Fox and Rubin in 68, and more comprehensively in Dharmadhikari, Nadkarni in 1960. They provided the first examples of processes that have finite Frankel rank, but require infinite classical memory. In fact, they were defined as functions of an infinite Markov chain, infinite memory Markov chain. And the proofs are particular. They use so-called Perron-Frobenius theories, or spectral information about the maps. And so you can ask a weaker question, or like a more permissive question. So if the process has a finite has a finite quasi-realization, can it be at least generated by a hidden quantum Markov model? And so this, you can say this is like basically the question of Hannes, Nachtigall, and Werner for the case of processes. And so one of the things we found in this work with Fanitza and Lumbreras is that actually Fox and Rubins, and then the more general class of processes by Dharmadhikari and Nadkarni, they all have hidden quantum Markov models. Without wanting to, they just happen to come across processes that can be realized with qubits. And so, yeah, I just want to come to the last bit, the separation. So I hope you can give me a couple more minutes to finish this. So one of the things that we realized is from the minimum dimension quasi-realization, which you can construct from the process itself, from its Hankel matrix, you can actually see some signature where it comes from. So in particular, this cone this positive cone that justifies the positivity of the probability law. This is obtained kind of quotienting down from the original hidden Markov or quantum Markov model. So in particular, if we have a process that has a positive realization, then a stable cone must exist, which is polyhedral. And if we have a quantum hidden Markov realization, then a cone must exist, a stable cone must exist that is well definable by semi-definite programming. So the C is basically the domain of a semi-definite program. And so in the example in the previous example that I showed, we actually designed in such a way that the minimum and the maximum possible cones are the same. And so we just have to look at it, is it polyhedral or not, to decide whether this process has a hidden Markov model or not. And so, well, okay, it's the Bloch sphere, so has infinitely many extremal points, so it's clearly not a polyhedron. So this has no finite classical realization. So it's a different way, I mean, like compared to Dharmadhikari and Nadkarni, we use the geometrical reasoning to argue that this cone, this process cannot have a classical realization, even though it's defined to have a quantum realization. And so we use the same kind of idea in the more recent work with Fanitza and Lumbreras. There exists a process with Hankel rank 3, which is the smallest possible. Again, min and maximum cone equal, and actually they are transcendental cones. So this proves that we cannot have a quantum realization because those semi-definite representable cones are actually definable by algebraic equations and inequalities. And so this proves geometrically this process cannot have a hidden quantum Markov model. And so this finally answers this open question from more than 30 years ago from the Hannes, Nachtigall, and Werner paper. There are finitely correlated states, actually even stochastic processes that are finitely correlated, but they cannot be defined using a quantum memory, any finite quantum memory. And so instead of showing you the process, because I'm out of time, which is a shame because it's very simple. I mean, it uses this kind of block how do you call this, Jordan structure of matrices. So when we multiply them, we multiply the diagonal elements, but in the Jordan block we actually add off diagonal elements, and so we can realize both addition and multiplication. Exponentiation and the linear function. So that's kind of where the transcendental nature comes from. Yeah, so this is all about the construction. So this example, it gives rise to a cone which actually exists in the literature already, the so-called exponential cone. It's written like this one here. This is actually the positive cone of this GPT. I didn't give you the unit. That's just an element in that cone. And then the dual cone is of a similar form, and the state space is simply all the positive linear functions that are 1 on the unit. In the paper, we also discussed some other classes. There is this so-called power cone, which has this law here: x to the t, y to the 1 minus t is larger than z. And this is also a transcendental cone if t is irrational, and it's a semi-algebraic cone if t is a rational number. Okay, and so there are lots of open questions, which I probably have to select a little bit which one I want to highlight. Well, maybe it's basically this one here, the one in yellow. So our argument just shows that there is no finite quantum memory and quantum process, like a quantum instrument, that would generate the entire infinitely long stochastic process. Yeah, so like what it says is, if you observe it long enough, you will notice, you will eventually notice deviation from any hypothetical quantum mechanism you have invented. But it doesn't say how long you have to wait for it. Like, I mean, and here's in yellow, this is kind of the question that tries to quantify this. So to approximate p on a temporal horizon of n, and up to an error epsilon, which might be, your stochastic error, the statistical error that you tolerate, how large of a virtual dimension do you need? And does that diverge when n goes to infinity, or does epsilon have to go to 0, or does it just remain? Is it also possible when epsilon goes bounded away from 1? And yeah, so there are plenty of other questions, but I think I'll just leave it here. Yeah, maybe this is another really nice one. So one of the reasons why Farnes, Nachtigall, and Werner and everybody else loved C-star finitely correlated states is because they have purifications. That's because completely positive maps by Steinspring theorem can be purified to isometries. You can always enlarge the system and make everything isometric, and then you get a matrix product state. So there's a kind of we have very concrete example of finitely correlated states, actually processes. Do they have finitely correlated purifications? That's completely open. Okay, and that's the end of the talk. Thank you very much, and thanks for the patience too.
Thank you very much, Andreas. And I'm sure there are plenty of questions, but unfortunately, we have completely run out of time. So maybe
yeah, I know. I'm sorry.
a very quick question.
Thank you, Andreas. Your talk was nice and it is mathematical. I appreciate it. And what I have understood from your talk that you have discussed about hidden Markov model, which means evolution of observable events when the underlying factors are actually not directly observable. So I have 3 questions for you. First question is, am I right?
Yes.
Yeah. So my first question, this hidden Markov model, does it have anything to do with the hidden state variable model, or it's something different?
Well, only in the sense that it's meant to be not directly observable.
Okay.
Yeah. But it's not like a foundational thing. I mean, like obviously, we think that we model it as a real system, which may be I mean, in principle, could, like in a hidden Markov process, in principle could be observed. There would be nothing wrong with that. We would not violate any kind of fundamental principles. It's just that from the point of the statistician, when you try to model a system, you know that what you observe is not identical to the full set of dynamical variables of the system. So there's like, I think sometimes people call them latent variables. So things that evolve, but you don't directly observe them.
And my second question is, just like hidden Markov model, have you worked on anything like non-Markov hidden model or something like that?
I've thought about this a little bit, but I don't have any results. No. No. The reason why we do this here, this is precisely because those are the simple ones, right? I mean, we have matrix product states because they are in some sense, they have memory, but it's like the most benign kind of memory. So we study matrix processing because we want to see how far we can get with it. But of course, it's a very important question, like how can we modify the model? So yeah, the non-Markovianity basically has to do with observation, right? Like, I mean, in the hidden Markov model, the latent variables, they evolve Markovianly, but then what you observe can be highly non-Markovian, because when you observe something at time u, it can be highly correlated with things that arrive in much later time, because there was this internal memory X that preserved this correlation until there came the moment to release it into the observable part. Yeah, so those the HMMs, they are already highly non-Markovian. It's just that they can be explained by lifting them to a Markovian one.
Okay, understood. And my last question is that in your slide you have only mentioned about the stochastic birth process. So I mean, what about stochastic death process? I mean, like.
Well, it's the same kind of thing. I mean, obviously, each moment of birth is when the process is reset. Yeah, so in the paper we call it a resetting process. Resetting. When you observe the zero, you know that the entire previous history has been erased, and the internal state of the system has been reset to something that you perfectly know well. It restarts again at a particular point. So in that sense, the memory is not infinitely long. It is potentially infinitely long, but once in a while, this zero appears, and then you know, oh, this is the end of the previous history, and now a completely new one begins, and there's no correlation between them.
Okay, so let us thank Andreas once again for your time and a very nice talk.
Thank you very much. Thanks also for the nice talks. I was following a little bit, but not too much today.
Thanks.
If there are more questions, please write to me, actually.
Yes, so please write to all of you students where we have more questions. So it's welcoming you.
Thank you. Thank you.
Thank you, Walter.
Oops, I will stop sharing now.
So now time for the next talk, which is by Dr. Soumya Das. And he's also on. Okay. So he's from Eindhoven Institute of Technology. So could you, so very nice. So let us see whether we can hear you.
Can you hear me?
Yeah, good enough. Yeah. So Soumya, you have half an hour for this, and so please.
Okay, so let me. So thank you for the opportunity to present this talk. So myself, Soumya, I am working as a postdoc in Eindhoven University of Technology in Netherlands. So my talk is on entanglement monogamy in indistinguishable particle systems. So this talk is based on the following paper. One is from my PhD with Professor Paul and Anindya from CQT Singapore, and this is another one is the follow-up one with Professor Rito from ISR, Bhubaneswar. So I will briefly introduce the problem statement, the introduction of indistinguishable particle, some of the background work, and then we will do the violation of monogamy for indistinguishable particle, the DOF trace-out rule, the monogamy for 3 or more indistinguishable particle, and finally I will conclude. So let us start with the introduction to indistinguishable or distinguishable particle. So let us see this particle list. So there are 2 types of particle. One is identical, one is non-identical. So 2 particles are said to be identical if they are identical on their all intrinsic properties such as mass, electric charge, spin, color. They are exactly the same. And if they are different from any of the property, we call them non-identical. So non-identical particles can be distinguished by that property, right? But we have identical particles that can we make either distinguishable or indistinguishable. So how we can do that? Okay, let us focus on the figure A. So there you can see 2 particles. We can label it, say, A and B based on their special wave function. So A is in special wave function, say, in this area S1, and B is concentrated in this area S2. Now we can differentiate. Now, say A and B are very much like identical. So identical in their all properties. But since they are in 2 space, physically located 2 space, we can make them distinguishable by this label S1 and S2. So we can say the particle is in S1 is A, the particle is in S2 is B. Now, if we make the particle very close enough, say in this particle S3, then you can say this labeling is gone. So you cannot really identify which particle is A and which particle is B. So this is the fundamental way of doing 2 identical particle, either distinguishable or indistinguishable. Now from figure B, if we again make these 2 particles apart, we cannot still distinguish these 2 particles, right? So they become indistinguishable after this mixing. Right. So now what were the related works around this distinguishable and indistinguishable particles? So most of the work in quantum information processing that we know, application and properties, they are basically using distinguishable particles, right? But in last say 10 to 20 years, there are lots of interest in indistinguishable particles. So for example, like quantum teleportation, as we know, that normally done using distinguishable particle, that was proposed and done using indistinguishable particle in 2018. Similarly, EPR steering, that is also known for distinguishable particle property, that is done for indistinguishable particle, again 2018. Entanglement swapping, that is known for distinguishable particle, that can also be done by indistinguishable particles, that is proposed in 2009. But not only from distinguishable to indistinguishable, there are some properties like duality of entanglement, they proposed by Sugatoda in 2013, and that is firstly known for indistinguishable particle, but later it is also done for distinguishable particle in 2006. So from this work, we can see that some properties are for distinguishable, they are later done for indistinguishable. Some are unique for indistinguishable, they are later for distinguishable. So there are some open questions like, is there any properties or correlation that is unique to only indistinguishable or only distinguishable particles, so that we can definitely identify these are indistinguishable, these are distinguishable. So that thing was done as a part of my first PhD work. So we find out two important properties for distinguishable and indistinguishable particle. They are unique to them only. So unit fidelity quantum teleportation. We have found out that quantum teleportation with unit fidelity, they are only possible for distinguishable particles. And hyperhybrid entangled state, this is a kind of special state that I will discuss later. This is only possible for indistinguishable particles. So previously, we have known some of the properties that belong to the overlap of these two sets, right? So with both distinguishable and indistinguishable. But we have proposed that there are some properties in this list for distinguishable sets, some properties are indistinguishable sets, right? So that is the related work. Now there are some question like, is there any fundamental property that is unique to this distinguishable and indistinguishable particle that we can definitely identify, right? Okay, so in search of the answer, let's talk about the monogamy. So we know what is the monogamy property. Monogamy is a rule that we can only marry one partner or one spouse, and multiple marriages are not available. Interestingly, this property is also holds for quantum particle where we have the properties of monogamy or entanglement. So it means that if two particles are entangled maximally, then they cannot have any more entanglement with other particles. And the entanglement between A and B and A and C are obviously bounded the total entanglement between A and the subsystem B and C. So this is like most of the as well known for monogamy, and this property is important because this is used for the security of quantum key distribution. So QKD is, we know that it is the most applied properties of quantum information. So this is the reason why we have the security of QKD, one of the reasons. And it is applicable for some classification of quantum state, black hole physics, condensed matter, etc. Now, does this monogamy hold? Now, the monogamy property depends on two things. One is the dimension of the particle and the entanglement measure. For example, we know that for concurrence measure, monogamy of entanglement for 2-qubit system holds. But for Q-trace system, this does not hold. So we need a different entanglement measure to measure this monogamy, right? Now comes to the maximum violation of monogamy. What is meant by the maximum violation? So when this, so for all entanglement measures, say E, this is bounded by the maximum value of entanglement, right? So suppose E of AB, it is bounded by some maximum value, say Emax. E of AC is bounded by Emax, then the total will be more than Emax. It is possible, right? So this is as non-maximum violation. But we are interested to the maximum violation. Well, all these E of AB and E of AC, they obtain the maximum value. So when the condition for equation 3 occurs, we say that the maximum violation of monogamy. Now there is an interesting relation between cloning and monogamy. We know that cloning has different meaning than the biologist. Biologist can clone anything or any sheep or any living element. But for quantum physicists, we cannot arbitrarily clone any unknown object, right? So there is a famous no cloning theorem that forbids the creation of an independent and identical copy of any unknown arbitrary quantum states, and it has like application in error correction and cryptography. Now, is there any relation between monogamy and cloning? Yes. If suppose we have a system where maximum violation of monogamy is possible, right? So that implies that we can clone any arbitrary quantum objects, right? But using distinguishable particles. How that can be done? Suppose A and B are maximally entangled, A and C are maximally entangled, and we have unknown quantum state phi x. We will do the Bell measurement with phi x and A, and based on the output B, we will do some unitary on B and C, and then we have two copies of B and C. Obviously, this we cannot done using distinguishable particle, so then it will violate the no cloning theorem, right? But so the question is this property holds for indistinguishable particle also? Let's go to some other scenario where particles are made by different degrees of freedom. Suppose B has 2 degrees of freedom 1, 2, A has 2 degrees of freedom 1, 2, C has 2 degrees of freedom 1, 2. Now suppose B1 is maximally entangled with A, A2 is maximally entangled with C. Now if we go to the particle view, we can see A and B and A and C are 2 maximally entangled. But this is not the case. We have to go to the degree of freedom view to actually show, like, if B1 or A1 are maximally entangled, then if E1 or C2 are maximally entangled, then we can say it is actually violating the monogamy of entanglement maximally. So we have to redefine our picture, like for monogamy, say the ith degree of freedom of A is maximally entangled with jth degrees of freedom of B, then ith degree of freedom of A cannot be maximally entangled with any kth degrees of freedom of B. And obviously they both are bounded. Right? Now, suppose for indistinguishable particle system, say for two particle system A and B, if we have to show that maximally entanglement occurs for indistinguishable particle, what we have to show, as we say, suppose A1 or B1 are spin or polarization entangled, A2 or B2 are path entangled, then we have to show like A1 and B1 and A1 or B2 are both maximally entangled, like A1, B1 and A1 and B2. Interestingly, to do this thing, we have to do the trace out rule. Now, trace out rule for particle system is already known for distinguishable particle, and that can be extended trivially for distinguishable particle with multiple DOF. Now, the trace out rule for indistinguishable particle was proposed by Lo-Franco et al. In 2005. But for indistinguishable particle system, multiple DOF, this degree trace out rule was not known. That we proposed for the first time. So if we have two particles with two DOF, we can write in this formulation in equation 6. I'm not going into the details. Then we can actually trace out any DOF from any particle using this complicated equation. And this is, you know, that for two particle, two DOF system. And this can be extended for like P particle and N DOF system. And that will be huge, and I'm not explaining that. So what we have found, there exists a circuit that was proposed by Lee et al., where using two particle and two DOF, we can show that maximum violation of monogamy is actually possible, right? So this is two particles, say Alice and Bob, and they are performing this particle exchange mechanism to make their particles indistinguishable, and they can measure either spin measurement or path measurement. So they have two DOF, either spin DOF or path DOF. So Alice can do this and Bob can do that. So if they can do that, we have mathematically found, because this circuits is made only linear optics. So mathematically found using concurrence measure, like the spin DOF of A and spin DOF of B is maximally entangled with concurrence entanglement measure, and spin DOF of A and the path DOF of B is also maximally entangled. So here we have find out one example where using indistinguishable particle system, we have found E1 and B1 are maximally entangled, E1 or B2 are also maximally entangled. So this is like a result that for indistinguishable particle system, maximally entanglement violation is possible, right? So this gives our some theorem that for qubit system. So we have done this only qubit system. Indistinguishability is a necessary criterion for maximum violation of monogamy entanglement by the same measures that are monogamous for distinguishable particles. Now, why qubit system? Because for qubit system, the monogamy of entanglement is valid for using concurrence measure. So we have chosen, because this is a strict rule, that in qubit system, monogamy of entanglement for concurrence measure cannot be violated, and maximum monogamy is not also cannot be violated. So we have shown this for this system. Obviously, it is a question that for higher dimensional system, this is valid or not. This is a like future work. So there are some open questions. Now, as we see, like for no cloning is similar to monogamy of entanglement for distinguishable particle system. Now we see for indistinguishable particle system, monogamy of entanglement or maximum violation of monogamy of entanglement is possible. But that does not lead to the violation of no cloning theory. So which one is more fundamental? For us, we think that no cloning theorem is more fundamental because it applies to distinguishable and indistinguishable particles. But monogamy of entanglement only applies to distinguishable particle system. Now, what will be the application of this violation? That we have to find out. We are still searching, is there some application for this? And is it possible, like there are other correlations like steering, coherence, discord, so where monogamy are sometimes obeyed, right? So is this maximum violation are also can be shown for other entanglement measures, right? So these are the open questions that we are searching. And based on this discussion, so we saw that we are only selected two particle system, like two particle, two DOF. So what is the picture now? For two particle, two DOF, for distinguishable particle, monogamy holds. For more than three particle, the monogamy holds. For two particle, two DOF system, indistinguishable setting can violate maximally. But for three particle and two DOF or multiple DOF, what is the situation? So this is the open question that we followed up, and we try to address this question. So we have found out that for three or more indistinguishable particle system having arbitrarily large number of degrees of freedom, they obey the monogamy of entanglement using this squared concurrence that we have previously used, right? So by that process, we have found out another result that if monogamy calculated for three or more indistinguishable particle, then for pure state, we have earlier shown that here you can see that there is an inequality, right? So AB and AC is less than or equal to for this system. So this inequality holds for pure state and both for mixed state, right? But if what we have found out that for indistinguishable particle system, for 3 or more particles, for pure state, this inequality becomes equality. Right. So A, B, and AC for different D wave, they are not unequal for pure system. But we have shown that for mixed system, for mixed indistinguishable set, again this inequality holds. So what is the overall picture now? The overall picture is okay. So for pure distinguishable state, the inequality holds. For mixed distinguishable state, inequality holds. But for pure indistinguishable state, the equality holds. But for mixed indistinguishable state, so inequality. So there comes another distinguished property or unique property for indistinguishable particle. Right. So this gives a nice relation between the purity, indistinguishability, and monogamy. So this is the first time they are like looking different property can be connected, right? So how they are connected? Suppose we have a pure and indistinguishable particle system, right? Then we show that monogamy equality always holds, right? Now we go to the case 2. Suppose we have an unknown pure state, right? Then we can measure whether the monogamy equality holds. If the equality does not hold, we have a direct answer that the states are made of distinguishable particles. But the answer is yes, then we have multiple possibilities as we show. Like monogamy equality does not hold, then we have multiple options. Either this one or this one, right? For unknown pure state. So we cannot conclusively say what it will be the unknown state. Now say case 3, we have an unknown state made of indistinguishable particles. Now we ask, does monogamy hold? If no, then the state is mixed. Right, because monogamy equality does not hold, then the state is obviously mixed. So it goes to here, the fourth one. But the answer is yes, then again we have multiple conclusions possible. And finally, we have unknown state. Is monogamy equality holds? No. Then the state cannot be both pure and indistinguishable particle. But if the monogamy equality holds, then multiple questions possible. So you can see that.
Sorry to interrupt. You have 5 more minutes to complete it.
Thank you.
Question.
Yeah. So we can see that this picture is actually incomplete, right? So, but we have a nice relation between purity, indistinguishability, and monogamy. So one of the future work will be to complete this picture, where from multiple questions we can definitely answer this thing, right? So this is so I have not discussed how we have proved the monogamy for 3 or more indistinguishable particles, each having n DOA. So in the paper, we can see the proof is not straightforward. So we have to analyze 13 different cases and do some rigorous mathematics to prove this thing. So unfortunately, there is no easy way to prove this. So if anybody is interested, they can look into the paper for the proof. And so the discussion is, since monogamy holds for 3 or more indistinguishable particles and inequality becomes equality for pure, as we say. So the connection between the monogamy purity that we have established, but the full characterization is an open area of research, right? So this is what we have found, and there are multiple open areas that we can look into. If anybody is interested, you can contact me. And since I have few more minutes left, I will discuss what the works currently I'm doing in my postdoc, what are the problems that we are analyzing. So the first work I'm currently analyzing the security analysis of continuous variable quantum key distribution system. So we know that for continuous CVQKD system, the security using Gaussian modulation is solved. But for discrete modulation is 256, either 64, the security is still an open issue. Right. So we have find out an easy solution for this Gaussian modulation system that we are aiming to apply for this discrete modulation system to solve this issue. So this is still an open area, and we are hopeful that we can close this issue. So this is one of my work in my postdocs. And recently, this quantum test beds, all these quantum test beds are available, and one of the contender or competitor of QKD is PQC. So there are lots of deployed use case of QKD, but there are no comparative analysis where QKD is used, PQC cannot be used. So we have written a comparative analysis of all the deployed use case. We have analyzed all the use case from different research article, from literature, from the different test bed, Madrid test bed, or test bed, and critically analyzed from which test bed QKD can be used, for which test bed PQC can be used, because that is a debate whether we can use QKD, or can use QKD, or we can use a hybrid. So that the paper we have archived. So if anybody want, they can have a look. And the third work that we are currently doing, the security analysis. So at Eindhoven, we have established a quantum communication test bed, and we have used a hybrid approach, both QKD and PQC. And I am doing a security analysis of the both QKD test bed. Like we have authentication layer, key distribution layer, and the data transfer layer. So all these layers, a practical security analysis is needed, right? So that's what I am currently doing for my PhD works, and that paper will also be archived soon.
I'm sorry,
And
run out of time.
yeah, sure. The last point. And the last one that we are currently doing for QRNG, for quantum random number generator, there are some evaluation of quantumness, efficiency, and cost. So that paper is also archived. So if you have a look, you can have a look on this paper. So thank you, sir, for your presentation, for your kind attention. And if you have any questions, so I am happy to answer.
Yeah, thank you so much. So, are there any questions? Okay, maybe let me ask you some naive question. So for indistinguishable particles, so there is a spin statistics connection, and you have to may require to either symmetrize or anti-symmetrize the wave function in order to deal with such situation. So in your analysis, do you actually take into account that?
Yes. In our analysis, so we have considered the state formulation here. So here in the equation 6, you can see there is a new term. So if the nu is 1, then it is symmetrized. If the nu is -1, that is anti-symmetrized. So
Okay,
this
thank you.
formulation is taken here.
The results that you obtained regarding monogamy or their violation,
Yes.
are they obtainable for both fermionic as well as bosonic systems?
Yes.
Same way.
Yes.
There is no difference between the magnitude of.
No. This can be done for both bosonic and fermionic systems.
And for multipartite systems, in certain cases, you showed that there are, the equality holds for certain states. So the equality also holds for both any kind of statistics?
Yes. This equality holds for any kind of statistics.
Okay, thank you. So if there are no more questions, let us thank the speaker once again for the very nice talk.
Thank you.
So we'll come back at 5 then.
Hello,
Yes, sir.
can you hear me?
Yes, you are audible. Can you please share your screen? We just want to check.
Sure. Okay. Let me try.
Yes, it is visible.
Visible. I don't know how about the. Let me just make small this. I need sorry. I need how to use the switch for slides. Just for me. I want to check. If I have a full screen, is it visible now?
Yes, it's visible. Yes, it's also changing.
It moves. It's changing. Okay, good.
And your voice is perfect. So we are
Okay.
having a tea break. So we'll join in 5 minutes.
Okay.
Okay.
So I want to make sure. So I'm prepared for 25 minutes plus 5 minutes question. Is it this?
Yes.
Okay, good. I have to be sharp. I mean, it is between my teaching classes, and I'm like,
Okay. We'll make sure.
exactly. I should start at 2, but I wrote to my students that I may be 10 minutes late.
Sure.
Okay, for switching, but I will answer questions surely.
Okay.
And apologize, I'm not in person. I was in the resource quantum resources workshop, and simply it was a week before or about that, and I decided, like, I have family, so I decided it's not good to travel so much one after the other.
No, it's fine, sir. It's fine. Okay, so we'll join in 5 minutes. So
Okay, I'm waiting here. Thank you.
okay.
Hi, Carol. Just 2 minutes more.
Oh, thanks.
Yeah, great. So thank you very much. Great to have you here on online, Carol. And let me formally, should we wait for, we can start. It's already 5. Yes. Yeah. So let us welcome Carol Horodetsky, who will be giving us the talk. He's at the University of Gdańsk. And you have half an hour for your talk.
Okay.
Some
Thank
time
you. Yeah.
Then there may be some questions.
Sure. And thank you for the introduction. It's a pleasure to be part of this event. I apologize, I'm online only. I would like to tell you about upper bounds on secret key rate in quantum scenarios. I'm just struggling here with the want to hide the okay, the bar. I'll try to work with this. Okay, so I will talk about 4 different cryptographic scenarios, and I will try to introduce them to you in a bit abstract way. So please forgive me this. The first slide will be already like shocking. So what is the key rate and what's the distillable key and what's the secret key? So the scenario is very traditional. So there is Alice, Bob, and Eve. They can talk via classical channel, and they want to distribute a secret key, have a secret key between each other, and this is a random bit string known only to them. So it's a very traditional task, but this can happen in many scenarios. So in abstract way, we can say that the parties, in order to do that, share tripartite objects. They can be states, devices, and so on, you will see. And in abstract way, we can say that distillable key is very informal. The distillable key of such an object that is shared is supremum of the ratio of the key obtained versus key bits versus number of the objects used by a protocol, which is some protocol comes from the set of allowed operations, and the protocol transforms end objects into something epsilon close to the secret key of length k. And we mean here for large n and small epsilon, of course, epsilon going to 0. So this is a bit tough definition, very abstract and informal, so it may be confusing. I will tell you more about the scenarios in a minute. So what are the scenarios I want to talk about? Sorry, I'm trying to switch the slide, but they're not switching. Okay, good. So these are the icons. Please remember them. I will use them through the talk. So there's classical secure key agreement scenario, device-dependent quantum cryptography, device-independent quantum cryptography, and non-signaling device-independent cryptography. Sorry, I'm trying to get rid of the bar, which I'm not used to. I can hide this panel. Okay, nice. Great. So from the left to right, there grows the paranoia, which is of course professional and well understood, because the power of eavesdropper grows here. And let's start with secure key agreement. Here, the objects that the parties share are triples of random variables. Alice and Bob share A, B, and Eve shares random variable E with total distribution P, A, B, E. And the allowed operations are local classical operations and public communication. Excuse me for that. Then the trust is that honest parties share PAB, and Eve knows only E with total PAB distribution about them. Right, so this is the drawing, and the resource here is partially ticket correlations, and key SKA is distillable key. Now, quantum device dependent scenario here, it's like you can think about BBT4 protocols. So the shared objects are tripartite quantum states. Allowed operations are local quantum operations and classical communication. It is convenient to use this class for upper bounds. And the trust is the dimension of the input state and the operations they use. It is not necessarily M, the measurement, but it is maybe some protocol. So they share these pure quantum states, and the resource is quantum entanglement, surely because separable states are insecure. And KDD is device-dependent key for me for this talk. Okay, device-independent scenario. Here we really worry about the fact that maybe we bought device that is not working according to specification. So the shared object is quantum extension of conditional probability distribution, because the parties only trust, Alice and Bob only trust inputs and outputs. inputs are X, Y, outputs are A and B. And the device they share between the honest parties share device, which is the probability distribution computed by local POVMs. The family of POVMs MX with outcomes A is for Alice, and family of POVMs MY with outcomes B for each Y is for Bob. And it holds the purifying system. They can process these classical outcomes by some local maps, classical operations, and publicly communicate. And so they trust that that device is quantum. So there exists some quantum underlying state and measurements, but otherwise they don't trust it. So possible attack is that if the operator is using local different POVMs, NXA, NYB, on a different state sigma, but such that statistics trace with these POVMs with sigma are the same as trace the POVMs M with rho. So notation N sigma is attacking device, and rho M is a honest implementation of a device. All right, so the total three parties share kind of an assemblage. Alice and Bob share device, and Eve has a conditional state, of course, in such a way that they cannot signal to them. There is no instantaneous change of the state of Eve upon their actions, and vice versa. And here, the resource is Bell locality, and KDI is device-independent distillable key. Good. Now, the non-signaling device-independent scenario, the most paranoid one, shared objects are conditional probability distributions, PABE given X, Y, Z, and allowed operations that are kind of safe to use are direct measurements in parallel. So when you have n objects, you measure them all together at once, because if there are forward correlations, I mean, there are attacks on such devices. And after this measurement, parallel measurement, you can process it by local classical operations and public communication. Here, even the physics of devices unknown. It may not be quantum, it may be some quantum future quantum gravity, whatever. The only assumption is that devices do not instantaneously send communication to Eve and vice versa. So this is a non-signaling assumption, right? So the joint tripartite object is this PABE given XYZ, conditional probability distribution. And again, some of these devices can be created from quantum correlations by honest producer. So Bell non-locality is a resource. And KNSDI is a non-signaling device-independent distillable key for me. So how well they perform, how many beats they get per n devices. Okay, so now it's time for lead motivation and outlook. We know I think, some lower bounds on secret key achievable by some protocols like BB84, and they're even realized in practice. But I'm interested in upper bounds that can tell about optimality of these protocols. So, I would like to ask the question: what do we know about upper bounds on secret key rate on this distillable key in these 4 scenarios? And I would like to give you a brief overview of techniques for constructing them. I base partly on the review that you can find here, but also go beyond talking about multipartite case and non-signaling adversary. So let me start with secure key agreement. Historically, this is not fully historical approach I have on this talk, but most of it is. Part of it is for pedagogical reasons. I start here historically. So secret key agreement is bounded by intrinsic information. In secret key agreement scenario, the key is bounded by intrinsic information. And this function is defined like this. It is a conditional mutual information, a combination of Shannon entropies of 3 systems, A, B, and E. And it is minimized further over classical channels of Alice that transforms her share E, her random variable E, to E prime. It has been introduced by William Maurer and the whole setup of secure key agreement that Alice and Bob agree on some star and take the signals, radio signals from them. and if is also getting some signal, and they share tripartite distribution. And later with Stefan Wolf, he proved that this intrinsic information is an upper bound on amount of secure key in this scenario. And as you will see, this would be like a mother for this formula for next upper bounds in plenty of scenarios. So first, device-dependent key. Here, you can bound secure key by squash entanglement and relative entropy of entanglement. So device-dependent key is upper bounded by entanglement measures. Okay, so first bound was via relative entropy of entanglement. I will not talk much about that. It's just the kind of distinguishability of the n copies of rho from an insecure state sigma divided by n, measured by relative entropy kind of distance in asymptotic limit. So that was the first upper bound, but this second was used the so-called squashed entanglement. This is entanglement measure, which is an analog of intrinsic information, but in quantum domain. So it was introduced by Matthias Christian, I think, in his thesis, and then published with Andreas Winter. He published a paper. And it is defined in the following way. Instead of Shannon entropies, you just compute von Neumann entropies on this E' system that is an output of now quantum channel applied to the system E. And this is applied on a purifying system of Eve, because in this paradigm, as I told you, the shared object is a pure tripartite state. This is the worst case scenario. In quantum world, Eve can only have purification. Good. And then Matthias, in his thesis, proved that it is an upper bound on device-dependent key. So we already see the analogy. Now we can ask, what about a non-signaling adversary? And so I jump already to the most paranoid scenario. I will later tell you more about more interesting quantum device-independent case. But now, because of the analogy, I want to tell you about results regarding a non-signaling adversary, the most kind of paranoid case, which is this icon. Here, instead of purification, we can use a notion which is an analog, which is a complete extension. It is a tripartite device, which extends a bipartite device PAB given XY in such a way that from a share P E given Z, Eve can obtain any other non-signaling extension by some proper operation, by adding some dice and wirings. This has been defined in this paper, and we can use it to define an analog of squash entanglement, which is squash non-locality. This is nothing but intrinsic information computed on action of three parties on a complete extension of PABXY that turns this total tripartite distribution, complete extension, into a classical distribution so that you can compute this intrinsic information. So what are the actions of three parties? Alice and Bob choose the inputs X and Y, which is this MXY measurement on the device. They get outputs. And Eve can make arbitrary operation. She can attach some dice, do some wirings and post-processing. She gets the E' from her share PE given Z, and then they compute. We can compute intrinsic information on resulting this classical distribution. So the key secure against non-signaling Eve, KNSDI, is upper bounded by this squashed non-locality. There is no factor half here because there are classical distributions. Squashed entanglement needed half because in quantum case, singlet has mutual information too. So there are some differences, but this is pure in full analogy to the squash entanglement case and intrinsic information I'll tell you about. Now I want to tell you, so this function is hard to compute. There's some infimum, maximum, minimum, especially this minimum over all operations is hard to compute, but there is a nice observation that Marvin Shevsky did, my former doctoral student. That's first of all, squash non-locality is convex, and therefore this NSDI key is upper bounded by lower convex hull of plots that upper bound squash non-locality. So you can think each attack that you can think of is kind of a plot like this, and the other attack is like that. And you can take convex hull, and this orange curve is also an upper bound, a tighter upper bound on a non-signaling device-independent key. And this technique later can be used in you will see, in quantum device-independent case as well. So what are the results? First result is that locality is not sufficient for non-signaling secrecy in this paradigm. If you consider a device which is a mixture of Popescu-Rochlik and anti-Popescu-Rochlik blocks that are conditional probability distribution defined like I show on the right-hand side, then you get such a drawing. Please just focus on this red curve. This is the squashed non-locality ISQ, and interestingly, it vanishes at 0 in point epsilon 0.2, which means that there are quantum non-local devices with 0 key secret against non-signaling adversary when you measure devices in parallel. We conjecture that even if you had some wirings, there is no way, because if you start doing wirings, you open really bad attacks. So we believe it's like a no-go result, in the sense that you cannot distill from them any non-signaling device-independent key. This RHW is a Hungarian-evolved lower bound, but it is like post-quantum, so it cannot be quantum realized. So you can ask whether whether you can use it in quantum world. So then you can consider such a quantum realizable device with which comes from an isotropic state with parameter P, which is from the paper by Asin, Massar, and Pironio. And they found the bound, which is this purple dashed line. We have noticed that actually they optimized similar function, but without naming it, and just gave an attack. We optimize it in our way on this complete extension. We got this orange curve, and then we can convexify the two plots, and you get this red part, which is the tightest numerical bound by convexification method. And this purple line is a lower bound achieved by the protocol they propose. And the blue line, you can forget, it's just some suboptimal upper bound. Okay, so these are results for non-signaling adversary. And like I said, there were like earlier research and partly parallel that was covering 3 scenarios. I will talk about 2 of the results, about quantum device independent key distribution and a variant of non-signaling adversary as well. This is done by Init Kaur, Mark Wilde, and Andreas Winter. They considered first a non-signaling scenario when if has a quantum shares, kind of, not necessarily one quantum state, but like quantum, you can represent here by quantum extension, some kind of quantum extensions. That's called non-signaling extension. And so the Eve is weaker, but Alice and Bob are also stronger. And they proved that this intrinsic non-locality, which is supremum over measurements of Alice and Bob and the infimum over extensions of the conditional mutual information, quantum conditional mutual information of this classical A and B and quantum E and classical XY, is an upper bound on key in this scenario. So it's a bit different scenario from ours, but this is a quite powerful result. And next, they have analogous definition in the case when the non-signaling extension is totally quantum. So Alice and Bob are quantum, Eve is also quantum, and they are obtained from some quantum state rho ABE by local PUVMs. These honest PUVMs that we don't trust them. If is doing them for us, and you can choose your favorite distribution of inputs. And then for such extensions, if you just consider infimum over such extensions, then they call the functions quantum intrinsic non-locality, this top function. And they prove that this NQ is upper bound on quantum device independent key, the key that really matters now. There are experiments showing that it can be non-zero, have non-zero rate, and so on. It's very important, and it was first result in this domain. So, however, interestingly, these two measures are faithful, meaning they are non-zero for all non-local devices. So you cannot make it zero by you cannot prove that key is zero using these functions. And there is another technique that suffers the same problem but is strong enough to have some implications, is via reduced entanglement measures. So in this paper, we have shown that if you take a device-dependent key and compute it on the attacking state, so you take a device which is relied by measurement M on state rho, and you take attacking state, instead you are given attacking state sigma, and on the sigma are measurement N, then you take, if you take infimo over such attacks and compute device-dependent key on sigma, then total function reduced key is upper bound on device-independent key. We call this reduction, this infimum. So as a corollary, any upper bound on device-dependent key after reduction becomes an interesting upper bound, non-trivial upper bound on device-independent key. For example, you can reduce the entanglement measure that I told you about, the regularized relative entropy and the squash entanglement. You can reduce them in such a way by plugging in the attacking states that mimic statistics, because this is mimicking statistics, that statistics and sigma are indistinguishable from MRO by the honest parties. And from that, you can conclude that for some states, no matter which Bell inequality you use, how many inputs and outputs and so on, there are states that for which there is a huge gap between device-independent key and device-dependent one. Okay, now we go to bounds that are able to be more tight for specific protocols. So instead of mimicking the whole device, it's an observation by Rotem, Arnold Friedman, and Felix Leditsky. It's enough to mimic Bell inequality violation S and the quantum bit error rate, the two parameters that the parties test. And they prove an analytical upper bound, which is formulated after this paper, my paper with Init Kaur and Siddhartha Das, in such a form that this is, again, you see this is called quantum intrinsic information, taken from this paper by Christian and Kodors, computed now not only on attacking state, but also attacking measurements over such attacks that mimic the CHSH value, the value of violation of CHSH inequality, and quantum bit error rate. So, and this works for this key is defined for supreme over protocols where the key rounds are announced. So if has to know when the key is measured, that this is measured by x0, y equals 0, and taken from outputs of this measurement. Fine, but there is also an attack is taken from this paper on the choice of n sigma. But there is even a more powerful attack, which is called convex combination attack, from the paper by Farkas and Kodors, which is purely classical strategy, very powerful, though. It uses intrinsic information, so they split the device into a convex combination of local and non-local part, and they kind of observe that when Eve knows the inputs, then she can know the outputs of a local device, and she can keep them as her outputs. And when she does not know what they have, they just put question mark. And if you optimize this E later, you can achieve even this intrinsic information to be 0, which means that a non-locality is not sufficient. Quantum non-locality is not sufficient resource for standard device-independent secure key generation. And by standard, they mean that Eve knows from which inputs the key is generated, either it was announced or she got to know it. Okay, and then you can put the things together, because the bound by Rotem and Felix works in one regime and the bound by Farkas works in the other regime. But actually, what I've shown with Init and Siddhartha is that they are actually instances of optimization of the same functional that we independently introduced, that was introduced by Rotem and Felix. We call it CC squash entanglement. And it is, again, convex function, so you can have a convexification argument. We call it ECC squashed. This is exactly the function that I showed you before in previous slide. And it is actually lower bound to the approaches by convex combination attack and by quantum intrinsic information, and it is lower than convex hull of the plot. So you have a bound that works well in noise regime. Okay, I'm moving forward. Then, using all the techniques I told you, you can get first results for multipartite case, meaning the conference key agreement, secure key agreement. So we have taken multipartite squash entanglement as a measure. We reduce it. Also measure it locally by the parties to kind of get quantum intrinsic information, and reduce it by the attacks. So this is the multipartite squashed entanglement. Then you measure it by measurement L that mimic your measurement M, and compute it on the attacking state. And this is the upper bound in multipartite case. Here also in the independent related result, I think equivalent formally is by B. Philip and co-authors in this paper. Okay, and so you can enjoy the upper bounds, and for example, on the protocol by Ribeiro, Murta, and Wiener from 2018. And last thing I want to tell you, because I'm almost out of time, is that you can be also interested in upper bounds on key that are not tight, but they're interesting because they have operational meaning. So we kind of want to develop a resource theory of quantum secret key, because there are so many resource theories. Why not to do it? And let me show the paper. So in this article, we have defined the key cost, which is how much secure key you need to create a given quantum state by LOCC. And we upper bounded by KF and also regularized, which is KF as key of formation. It's an analog of entanglement of formation, where you split raw into ensembles of analogs of pure state in privacy regime. And we kind of show that there is a gap between KD and KC sometimes, and we have this nice sequence of inequalities. All right, so to summarize, I shown you the whole family of upper bounds. I just list them here for you. They were from different paradigms. They're very related, like most of them are like kits of intrinsic information in some way. What we know is that Fichte's proportional locality is like outperforms the convex combination and AFL bound, and this related also to the quantum intrinsic non-locality. They're not exactly equal, but they're very related. You can formulate one using the other. Okay, and I didn't say so much about relative entropy, but you can also deal with this. And with that, I conclude with open problems. There is a conjecture by Rotem and Felix that PPT states are useless for DISQIC. This is an open problem. We don't know if all entangled states are key distillable in device-dependent case. So if not non-locality, so what is a sufficient resource for DIQKD? Can we identify one? And any other new methods of upper bounding secret key are welcome. And with that, I would like to thank you for your attention.
Thank you very much. Time
I've used up most of the time, sorry.
Maybe we'll have some quick questions.
Yes.
Good afternoon, Carol. It's a nice talk. I have two questions for you. It's regarding the measure that you have mentioned, squashed entanglement. Now, if I'm wrong, you make me correct. Then what I know,
Yes.
Among several measures of entanglement, some measures are monogamous in nature and some are non-monogamous in nature. So like relative entropy of entanglement, so far as I know, it is non-monogamous in nature. So squashed entanglement, is it monogamous measure or is it non-monogamous measure?
It's a good question. I expect it is not. I think there is okay, I cannot say it's 100% sure, but I have a feeling that there is a paper by Andreas Winter about that if your state is extendable, like K extendable, so like you violate monogamy with K bobs, Alice with K bobs, okay? then the squashed entanglement goes down by a factor of 1 over k and some other factor. So it is kind of, in that sense, it's monogamous. So it's not that you can have, I think entanglement of formation is not monogamous, but the squashed in some sense is.
Okay. And my second question, the last question is that in your one of your slides, you have mentioned convex hull. So is it because the squashed entanglement is give you is no upper bound is there? So it's I mean, is it related to the measure? I mean, the convex hull, the geometry you are getting, is it related to squashed entanglement or some? I missed that.
It's just upper bound on it. So it's like we don't, because you look, this squashed entanglement is or squashed locality here. I meant you can do it the same for squashed entanglement. It is defined by this minimization. There is minimization of the action of Eve. So it is hard really to compute it. I don't know if people can. I mean, the squashed entanglement actually, the Favre brothers with Codor, they compute this, but this with measurements, I think it is not. We don't have a like easy numerics to do it. And what you can do, you can just plug in any attack, like get some E prime, compute the curve like this, and then compute the other attack, which is like that, and then you can just convexify them. And this orange curve is not yet the squashed non-locality or the squashed function, but it's just an upper bound on it, which is in turn an upper bound on the key. Okay, so that's the technique, right? I'm not sure I answered your question properly.
Hi, Carol. Yes, so I think the monogamy of squashed entanglement holds in general, like the CKW type that was given by Andras, Winter, and others.
Aha, okay, thanks. Yeah. Thanks for assuring this.
Thank you very much. So we are running short of time. So let us thank the speaker once again. Thank you very much for your time.
Thank you. Let me just
So we move
stop sharing.
Yeah, last talk of this session and this conference. Online, yeah, I know, but it is available on. Okay. So, confusion regarding the time or time zone. Yes, because while okay. What's the about? It is what? But you don't have his WhatsApp or anything. Yeah, let's wait for 5 minutes. Chat together. Polygon. Yeah.
Thank you. Yeah. Okay, so thank you very much for your patience. Okay, now it has been a long 3 days. Some of you are still here, so that itself you deserve some kind of medal for that. Okay, so if any one of you has, oh, he has joined. No? Okay, okay, take it. Okay, fine. So if you have learned from any of the talk posters or your interaction, then a lot of hard work that has been put in by some of the volunteers has paid off. Okay. So I think as a formality, I think I have to thank lots of people here. So I will start with our session chairmen. I mean, we had Professor Anirudh Pathak, then Professor R.P. Singh, and then Professor Devashish Sarkar, Professor Usha Devi, and Professor Devashish Ghosh, and Archan Majumdar. So they have to conduct a lot of these talks. So thank you all of them. Then from organizational perspective here. And from organizational point of view, first our director, TCG Press Director, Mr. Swapn Bhattacharya, for his support and encouragement. Then our secure director, Professor Bhanudas, he gave many ideas for this conference. Also, obviously, he encouraged and supported us. Then, of course, for organization and administrative support, Mr. Suprakash Das and his team, he gave many ideas, okay, how to organize things. Whenever there was a problem, we will go to him and he will find a solution. Then, of course, Mr. Ayanshu Banerjee and his team, most of the talks went through without any issue, so that was his team's, because of his team. Then, of course, this conference would not have been possible without the enthusiasm of many students. So without them, perhaps, things may have fallen apart. Okay, it was their enthusiasm which propelled this conference. So, okay, so you have already interacted with most of them. So I should name at least some of them, so that I don't forget any names. Okay, so these students like Mithun, Sobit, then we have Arnab, Akansha, Viplav, Anupam. Anupam is sitting there, I think, for all 3 days there. Arnab has been sitting here. And I think all of you have interacted with Sobit, wherever you are staying. Mithun has been doing behind the back, all this website. Viplav is also, so he has been also, our these talks, I mean, YouTube, still live streaming. Then you also Akansha, she also has played a major role, and Anumita, I think she is not here. Oh, where is she? Oh, she is here. Okay, okay, okay. So, and then Anupam, okay, and okay, and also Stanton have also played a major role. So let's thank at least all of them. Also mentioned 3-4 names from administration. Okay, first from academic, Professor Siddharth, is he here? No. Okay, he has played a major role in moving things around. Then, of course, Dr. Prasanjit, I don't know if he is here. And Snehal, Dr. Snehal, he has also played a major role in especially YouTube stream, live streaming. Then, of course, Mr. Devendra, he was behind a lot of this effort. Yeah, yeah, food and accommodation. And also Miss Polumi, our, friend, who will, he has handled a lot of administration. Okay, so all of these guys, deserve a lot of thanks. They made this conference possible. And all of you who came, if you would not have come, and I hope you have learned something here. You must have interacted with a lot of your other fellow students, a lot of stuff that I hope you will take. If you write some paper at some point because of learning something here, then okay. So thank you all for that. Yeah, yeah, right. No, I agree with you. So, Professor, one who is still here, from the beginning, no, 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 and also, thank you for, for the opportunity here. First, Berlin to the last. And then also we had outstation speaker. He had just left. Yeah, he was here until the very end. And also Professor Prem Kumar was there for a short time. Then other outstation speakers, but they were all, so I think, but they, yeah, they, yeah, yeah, they, I mean, well, I won't think some of the,